Hello there, welcome to the wonderful world of radio frequency and electronics engineering. Hope you're keeping well. Well, I've got a beauty on the bench today, a Marconi Instruments radio test set, 100 kHz to 1 GHz measurement range, and model number 2966A. So this is one of many of the models within the 2965 series of radio test instruments. Now, before I explain what all the models are and the variances between them exactly, the gentleman who brought this to me for repair brought it to me with the remark that it just didn't work. So that's all the information I have to go on. No other information other than that. So you're joining me at the moment after the video has already been filmed and we've reached the end of the repair, and what you're about to see can only be described as multiple crises. We go from one crisis to another a nightmare radio test set. And I won't give the game away at this point, but let me tell you, I'm not the only person that's worked on this test set, let's put it that way. And so what besets us is incredible difficulties as we go through this instrument, and that's the reason why this video is quite lengthy. And what you see with my videos is what you get in reality. So we're going to go on a journey in this video like no other, and we're going to explore all the little faults. This radio test set has so many faults on it that it's unbelievable. But anyway, we do actually find out what's wrong with the test instrument with one of the major faults which have occurred on this instrument. So bear with me in this video, you will enjoy it. It's a superb video for anybody who's wanting to try and repair one of these things, because they are quite a complex instrument. Anyway, let's get on with describing the models. So this is a 2966A. They all started with the Marconi 2965. Now the 2965 provides test facilities for mobile radios up to 1.05 GHz and mobile telephone testing, cellular test facilities, and analog systems as well for PMR, private mobile radio systems. The facilities are available on any particular instrument, which vary according to the options supplied with it. So the 2965 series of radio test set is a base model radio communications test instrument. Okay, so the 2965, just like this model, will have a TXRX test duplex. It'll do tone and signaling systems. Under the systems options, it will, depending on what's been software enabled, it will do various radio communication systems, from anything like MPT 1327 trunked, different other models radio systems that are specific, signaling standards. They can all be enabled under systems. Then we've also got AF and RF tests, and in the AF test we can also generate and receive audio frequencies and tones on these two ports, as well as through the multimeter connections here. So it's a full function multimeter. In the RF test option, we have the ability to listen to off-air signals through an external antenna connected to the TNC port, as well as being able to enable the track gen, because this test set comes as standard with the 2965, 65A, 66A, 67 and 68 come with tracking generators on them, and a spectrum analyzer as well. There's a spectrum analyzer mode you can go into under TX test in order to look at spectrum analyzer, either off air where you can look and listen via the TNC port, or obviously do the same with the type N port. Now on top of that as well, they also have board fitted, which is called AE8, most of these test sets, which allows SSB demodulation. The test sets come as standard with AM, FM and phase modulation, demodulation and modulation standards for the received signal generator, as well as the transmit analysis. but also within the software, and you can go into it through the help menu under options, system options, you can try and enable the SSB option, but it does ask for an unlock password to be entered. However, the test sets are fitted as standard with AE8, which is the SSB demodulator board, so it just needs enabling in the software if you can ever find the passcode. Now, they are a very versatile test set instrument. We all know, or most of us will, that the radio communications combined test set started with the Marconi 2955. The Marconi 2955 have various options that you could add to it with a little tray that went underneath, and that enabled it to be either a 2958, a 2960, I think a 2960, where you could have trunked and cellular standards added underneath, like a tray there, if I remember rightly. There's a 2955R, which had the sensitive receiver, off-air receiver option. So obviously that has this facility as well as a look and listen off-air receiver. And indeed there was a 2955B model, which was white fronted like this. And then we left the 2955 series of radio test sets then, and Marconi started producing the 2945, which we've seen on this channel, which has got a big LCD display here, a bit smaller than this test set. But that test set had all the facilities of the Marconi 2955 with some of the functionality of the 2965 series, with some added forensic options on there for like transient analysis. So the test sets were sort of evolving then. And then from the 2945 became the avionics version, the 2946, with ILS, VOR and directional beacon and ILS instrument landing system options on it. And then we hopped then to the 2965 series. So the 2965 is the base model for radio communication systems. The 2965A provides test facilities generally similar to the 2965 from which it is derived, but contains many differences to the mechanical design and the electronic hardware and software. It forms a basic platform of the 2966A, the 67 and the 68 series. So the 2966A instrument, which Marconi manual describes here that I'm reading, which is this model that we're looking at today, the 2966A provides test facilities for mobile radios up to 1.05 GHz and digital test facilities for some systems such as GSM 900. The 2967 provides test facilities for mobile radios up to 2 GHz and digital test facilities up to 2 GHz for systems such as GSM 900, GSM 1800 and GSM 1900. So that's got a bit of a split personality. It's got an extended frequency range up to 2 GHz because it has a frequency doubler in it, which allows us to do mobile radio testing. So that's really good for equipment above 1 GHz. And also it tests GSM 1800, 1900 MHz bands. And the 2968, which is a test that I have here on the bench behind this one we're looking at today, the 2968 provides test facilities for mobile radios up to 1.05 GHz and digital test facilities for mobiles and base stations on the Tetra system. So the 2968 is really the top model, other than the 2967, which has the extended frequency range up to 2 GHz. So there are, if you like, 5 models in the range: the 2965, the 65A, the 66A, the 67, and then the 68. And they're the 5 models of a 2960 series of radio test sets. Very versatile, very good. Has a power rating on the end port there up to 150 watts. If you have got the model which has the SSB enabled in the software, then you can do SSB receiver and transmitter testing, which is great for HF radios. Obviously we've got the usual functionality of the 2955 or 2945 and many of the other models in between. So this is like the bee's knees of the radio comms test sets that Marconi produced. Not only does it have a track gen on it and all the audio testing facilities and spectrum analyzer and everything else that's crammed into it, it's a very good fully functional radio test set. Really good radio test instrument to have on the bench, and that's why I have one here. Now this radio test set has apparently got a fault on it where it just doesn't work, so we're going to go through that now in the video, and we're going to see what is wrong with it. So hold tight, here we go. Okay, so we're connected up our cable to the Rohde & Schwarz radio test set. We have our transmitter source here, which is on a frequency of 145 megahertz dead. So we're going to key up the transmitter, and we're just going to check that RF power reading there, which as we can see is 4.85 watts, call it. So now we've done that, we're just going to now do the same with the other, the HP Agilent radio test set, and see what that reads. Again, we're on TX test on there, so we'll just try and zoom in to capture that. Okay, so the TX power will be on the top left of the screen, so we're getting 4.78 watts there, just a little bit less than what the Rohde & Schwarz was reading by tens of milliwatts or thereabouts. So we'll just keep going on. We'll just onto the Marconi. Measure this one. Right. So again, this is measured on the top right of the display. So we'll just keep up with the power. So we're getting 4.7 something watts, 79 watts or thereabouts with the look of it. Yeah, 4.7 something watts. So getting similar measurements across the board. So we'll now attach this same power source then to the Marconi radio test set, and we'll measure it on that and see what the customer was reported low TX power on it. So we'll just connect it up. Okay, so having seen that there's a discrepancy between my instruments and this instrument insofar as transmitter power is concerned, one of the things that we need to look at next is the calibration menu within the instrument to see whether we can do a self-calibration and enter that. That's one of the easiest ways to try and overcome any issues first of all. And how we access that is by pressing the help setup menu key here, and then that gets us into a menu. But when I press it, it doesn't work, unfortunately, nor does the AF test button work. With the RF test one works. We've got that where we can select SSB, and that option's not enabled on this particular one. Or we've got the RF in out test, RF analyzer test, so we can set up track gen or off air receiver there. That works. We've obviously got systems menu where we can set the different enabled radio systems that are enabled or disabled on the system in the radio test set, and I just can't seem to get those other keys working. And then obviously we've got the tones menu there as well, that works for different tone standards, etc. Then we've got the duplex test menu, that works, RX test, and obviously transmitter test, that works. But those two buttons are not working, and I need to get into that menu in order to get to the calibration mode. And there are self-test features within that as well, so it's ironic I can't get into that. Now I believe that's definitely responding. That is as well. Let's just check these side keys. There, that works. Yeah, that works. That works. That works. That works. That does. That does. That does. Yeah. that does, and that does, that does, that does, that does, that does as well. Yeah, so all the keys, they're all working. They all work apart from these two. Let's do transmitter, TX, that's it, frequency, increment, that works. That definitely works. Level, that's responding. That's responding. That is, that is, that is, that is, that is, that is. So yeah, they look all okay. That one does anyway. Yeah, they're all fine then. Just going to have a look at the numerical keys now, see whether they work. Let's just have a look. Right, let's have a look here. 0 point, and then yeah, they all work. That works as well between the different RF ports, as it should do. So everything's working apart from those two. Although hang on a second, I just need to check this. RF gen frequency increment 100 megahertz, RF gen level increment, I'll put that as 1 dB, and then when I hit the frequency increment decrement keys here, that should work. And it isn't, it's not advancing or decreasing by 100 megahertz as a frequency. If I go to the level and try and up and down the level, the RF level's not responding. However, the rotary control does, so that's there. So there's something not quite right about that. So in other words, there's 6 keys now, 2, 4, 6 keys there, that little group of keys there, which I find quite strange, because those 2 keys would share that column, and perhaps share a row with these side keys, although may not. And these 4 here would share that row, or that column if you like, and that column, and perhaps the same row again there. But I'm assuming those, it could be the rows are out rather than the columns, so it could be there's something strange going on. But as well as that, we've obviously got this banana socket here that's been pushed in and broken off. It should have a nice flange on it, and there is a cement resistor connector between those two on the inside as a current shunt for the ammeter, so maybe that's melted something perhaps, because that's certainly melted and broken off. I've also noticed something else as well. If you compare my test set behind, we've got the supply light on the top left, the amber LED. We don't have that on here, so I wonder if there's some connectivity issue perhaps between the digital control board and the front panel. Maybe there's some issue there, some damage has occurred, or something's become unplugged or disturbed, or maybe broken connection somewhere. So we can look into that a little bit further. But just to show you on my radio test set, what we'll be looking to get to on this one eventually, when we get the keyboard thing sorted out, is if you go to the help setup menu, in there you've obviously got the reset button there, which so you can essentially reset the instrument and put it back to manufacturer's defaults if you like. So if you mess any measurements up or anything in the instrument, you can always, you know, recover it that way. But if we go back into the help menu, there is user calibration, and then in there you'll see there's run broadband power and all that sort of jazz. So you can see there, look, on the top left. So that's what I'll be looking at. I know those calibration procedures are brought in by an internal cal standard within the instrument that's switched in, and then it goes through the routine of calibrating the DAC values to align it internally. So maybe that's you know, something that we could look at first once we get the keypad repaired. So that's one issue. Obviously the other button that didn't work was this one, which is the AF ANALYSER. You can select in there SSB if it's obviously enabled or whatever. Oh sorry, multimeter. You can select like a audio input output test, or you can select the multifunction multimeter, DVM, digital voltmeter. So that's something we couldn't access on this particular radio test set at the moment, so obviously we're going to have to look at that and and see what potentially could go wrong. So I'll have a look at some measurements now, what we can do next by looking at the RF outputs on here, because although the transmit monitor is out of spec, I'd be interested to see whether the receive signal generator is equally out of spec, because that might tell us something about whether it's a calibration issue or whether it's a TX attenuator power meter issue versus receive signal generator issue as well. So we'll need to look at that more in depth and find out, you know, do some RF testing now on the unit. But we'll just whip the lid off and have a look inside, see if there's anything obvious. You never know if somebody else has been in playing around, unplugging things, and let's do some basic fault finding first before we go any further. Okay, so just a quick rundown on the internals within the unit. What we've got this board here, which is the front panel interface unit. This has the calibrator on it for the RF power. So basically this circuit here produces a reference frequency. I think it's around about 50 megahertz at 0 dBm. That comes out on this coaxial cable and is fed into the RF attenuator switcher assembly here. We've also got the RF power meter module, which sits under this board. Various options for the different types of test instrument, the 29, 66, 65, 67, 68, etc. We'll have different modules fitted under there. When you remove this board, there's like a cage underneath with modules, RF modules that sit there. But the furthest on the right is always the same. That's the RF power meter module. So basically a sniff of the RF attenuator signal from the power, once it's been stripped down in level, comes here along this coaxial cable into the RF power detect module. So this basically detects RF power that sits under here, and that's the SMA connector for it there. So that's where the RF power meter is. Now on the side here we've got the input module for the RF. So in that is RF relays that switch between the N-type and the TNC on top. So we've got the N-type and TNC socket. So this switches the RF Sig Gen in appropriate duplex simplex operation, but it also has a pad in it, an attenuator pad rated to about 200 watts that reduces the TX power that's coming in the N-type socket way down to very low level, and that then is fed off then to what is the receiver unit within the test set, which then looks at the transmit analysis. Also there are different configurations that can be switched in on this with regards to RF level, and obviously there's an RF switch in there as well for switching in the calibrator path. So when it does its own calibration routine for RF power, it sets up a signal, as I've said earlier, which goes in on here, which then it switches in internally within itself to then measure itself, so then it can calibrate itself. And the calibrator output level is adjusted by this blue potentiometer there. Now there are software corrections as well as hardware corrections done for calibration. So throughout the instrument there are things that you can adjust, like potentiometers and capacitors, etc. And then also there are software calibrations, which we'll go into a bit later, which set up the RF power meter and various other things. Now if we just turn the test set around a little bit, we can see just how deep that RF attenuator assembly is. It's quite a big module, takes up nearly the full depth of a test instrument, and that's obviously quite an important thing, because all the RF signal, if you like, power is dealt with there for the transmitter as a load, and obviously then we've got the RF signal as well from the signal generator connecting in on that connector there, that SMA. We have a step attenuator like we do in most of radio test instruments, which is just a bit below. This is a step attenuator, and we've also got the memory backup battery module just fitted above it. Now this is quite a deep module, but that's a step attenuator for the RF signal generator. The RF signal generator comes in on the bottom and leaves on the top before then it goes off to the main dB attenuator pad up here, which is then obviously going to attenuate the signal again going out. So it's got to make up for it with RF level, obviously, in order to overcome that attenuation, because this has attenuation going out as well as coming in, because obviously it's the way it works with the transmit power has to be absorbed and reduced substantially while it's coming into this module for it to be measured at such low level. Likewise, in duplex mode, the RF Sig Gen needs to go out through it as well. So the RF Sig Gen level is actually quite high. It has to be, say if there's a 20 dB pad in there, it has to be 20 dBs higher than the expected output in order to overcome that loss. So that again is quite a big module, this RF attenuator module. It's again quite deep. When we're looking underneath there as well, we can see there's another module sandwiched in between. Now, depending whether it's a 29, 67, 68, 66, 65, depends what modules are fitted, because some test sets can increase the frequency range up to about 2 GHz to take in the higher optional bands that it can cover, which is for cellular systems at you know, up to 1800 MHz and above. So if the options are fitted on the test set when it's purchased, then these modules will be fitted as well. But you can see the basic 2965 that doesn't have cellular options on it without these modules in. And likewise, if I just try and sneak a view in under there, it's not very clear, but that module there, that frame at the top there, that is where the optional modules are installed. You can see that there's lugs there for them, so you can have, depending on what options you fit, there'll be modules in there, you see, that are fastened in, because this tray hinges out. And also there's modules that can be fitted in beneath there, which is these two, but also under this board here, there's another cage under there with modules that are fitted in there, like I alluded to earlier. So that's that. Now this is the RF tray assembly, and I've taken the cover off so you can see. So basically, as it comes down to it, we've got on the far left here, we've got the TX monitor demodulator board, which deals with AM, FM, SSB, which is the AE8 board, which is this that's fitted, and phase modulation. So all that's dealt with here, okay. And then on top of that as well, we've got a spectrum analyzer board, which is in the middle here. So the spectrum analyzer filters and things are dealt with by these crystal filters here. So that's just the basics of that. There are other boards as well which serve a dual function, which is on the other side, which you can't see at the moment, but they're basically the basic RF interface boards. Now these boards have got I2C controllers on them, and which are these ICs here. There's an IC there, and under the AE8 board there's another one, because this is the I2C control bus cables. So most of how the boards operate is developed from analog into digital conversion. So rather than dealing with analog signals directly, there's a lot of analog to digital control takes place on the board itself from the microcontroller. And then we've obviously got the main controller, the I2C controller, which sits at the bottom here, which then does all that control. On this side here, we've got sort of the oscillators for the main unit, so that we can generate frequencies for the signal generator. Then we've got, again, another local oscillator, which then mixes with an incoming signal here, to then be fed into what is the final amplifier module before being fed out. Now on the reverse side of this, which you can't see until you hinge this down, there are other modules as well which are in the intermediate section of the unit as well. So there's quite a bit to it really, but if we just go back round the other side a second, in this section here I alluded that there was other modules that are fitted under here, and I've got a little printout that I've done which tells us what that is. So the power module sits under there, which is that connector there, that's for the power meter. We've got, if you have GSM cellular options, things like that fitted, there's something called a warp oscillator, which is again another module that fits under there. and then there's another module which depends on what frequency ranges the cellular systems operate on, that are part of the options or system options that you purchase. So if it's above a 1 GHz normal frequency range for the test instruments, then you have what's called a down converter module. So you have a couple of different down converter modules fitted on this, but basically you had your power meter, your warp oscillator, and then your down converter module. And likewise on the other side, as I showed you, there are also optional modules that can go in there for different things. Now we've got the CRT display unit there, the cathode ray tube display unit, the adjustment potentiometers in the service manual tell you what all these little holes do, pots, etc. This board here just looks to be single board. It isn't, it's part of a cassette. When you undo these screws that are in place, this entire cassette moves and comes away, which you'll see later in the video, and that exposes then all the system cards. Now the system cards actually comprise of quite a few, depending on what the model of a test set is, depends on the cards that are installed here. So the very top board, which is this one, is called the A3 audio processor board. Then there's another board, there's like 7 boards all stacked in a cassette here. The next one under it is called the A2 board, audio processor board. Then there's another board under that called the A1, which is the audio gen board. Then there's another board under that which is called the A8 modem board, and then there's another board under that which is called the display board, which drives the CRT display that's character set and does scope measurements and various other things to do with auto ranging. And then under that is the A4 board, which is the PPH, RTP, TTP digital systems card. So if you've got Tetra on it, for example, or you've got DMR or other digital modes for cellular, then that card will change depending on what that option is. So that's the systems card, if you like. And then under that, which is when you remove this cassette, right at the bottom of a test set, which you see when you move this cassette out, is the CPU board, the main control board, which is called A6. Okay, right, so then the 10 megahertz reference oscillator board, or the test set's time base, is down here, and that's the TCXO temperature controlled or the OCXO board. That, so that board there is called the AR1. Now some of the boards share the measurement functions with others, so there's a process of analog to digital conversion takes place, and then that's then conveyed on the data bus via the main data bus there on the I2C bus, then to be shared with other boards, and then they interact with one another on a unidirectional asynchronous receiver transmitter serial interface. So they're constantly communicating with one another, and there are several DSPs on each board which convert analog to digital signal processing, and then that's then shared with obviously the control board, the display board, the audio processor, the audio gen, the modem, and all the other boards all share that data, and it's controlled that way. So it's quite a unique design in that sense. So that's where, you know, you end up then doing board swaps in order to fault find to more accurate level, because it's this board, for example, here, although it's labeled as the audio processor board, that does share some of its measurement functions with the board directly underneath, which is called the A2 audio A1 audio gen board. So the audio gen board and the audio processor board both use the same DSPs and talk to each other to do the same measurements. So in other words, when you're trying to fault find, you've got fault finding on more than one board for the same process, which needs to be looked at. So that's when things get quite complicated. However, these boards do come apart, and there is a hinge there, these little plastic hinges here. So if you wanted to get to the next board down, you undo these screws, and then this board lifts away as well in its own hinge. so you can get to the next board below. Now you can only do that for about 2 or 3 boards in depth, before then you would have to then try and take the cassette apart and try and lay boards down, and you'll see as well when you get this apart, there's another connector, which is this group of cables here, connects into the side of one of the boards, and these have to come off as well, the ones that are connected here, so to allow the cassette to come out, and it gets quite complicated, put it that way. So that's a little rundown of that. So it's quite well packed, I must admit. There's quite a bit to it, and there's lots of little things in between, sandwiched in between, but it all depends what model of test set you've got, because if you've got the 2965 basic test set, then you just have the basics inside. If you've got the 2966, 67, 68, then that's when all these extra modules and options get fitted, and the thing sort of gets crammed up then. So then the service manual refers to A2-1-2, for example, because the A2 board then is also a module and a PCB. So you've got an RF module and a PCB that are combined together in a measurement scenario. So as far as the system's concerned, so then you start delving off, and the manual breaks it down quite well in respect of that, but it gets more complicated the more modules and options that are added to it. So that's about it really. I don't think there's much else I can say. So on any repair that we do on a piece of equipment like this, any electronic equipment, is we should really always start with the power supply, because this is the heart of the instrument. Without the power supply, or the power supply rails being accurate that are coming from this unit, then the rest of the system won't work, and we'll go off down little rabbit warrens trying to find out you know, what's gone wrong with other things, and if we skip measuring the power supply first. So we don't want to work backwards to the power supply. If anything, we need to work forwards from the power supply onwards. So obviously this power supply is at the rear of the unit at the bottom here. Now in order to get into this, should this be faulty, we'd have to strip the back of the test set down to remove this module, which is quite a significant task in itself, very laborious. Now there are 2 different types of power supplies on this particular radio test set. There are AC only power supplies, and there's DC and AC power supplies. This one's a DC AC supply because it has a socket on the side for connecting to a battery, so you can run it from a battery in the field if you so wish to do so. So they're the 2 different variants of these power supplies. Now all the output rails for the power supply come out on this connector here, and so this is a breakout board, is this PCB for the power supply. So this connector, for example, goes off to the main microprocessor board, other connectors go off to other boards, fans, and then we've got a connector down here which goes off to some of the other system modules. So all the power is obtained from that little PCB there, and so we need to measure these pin number 1 to pin number 14 on this feed through connector in order to see what the supplies will be. Now according to technical description for the power supply, this is a technical description here, and as we can read there from the outputs from this supply, we've got basically a number of supplies, minus 5 volts at 2 amps, a plus 12 volt at 2 amps, and a 32 volt supply at 150 milliamps, which I believe is used for the CRT monitor supply actually. There's a plus 12 volt at 45 amps and a minus 12 volt at 2.5 amps. But in addition to this, obviously they all use a common ground principle, so that goes to the chassis rail of the test set, so we can use that for our minus 0 volt reference point. And then we've also got other supplies as well, which, well, we've got a 24 volt supply too for the cooling fan, which is fed to a 2-pin connector, and there's also a signal, a synchronization signal of 125 kilohertz, which is fed to the CPU board to lock the switch mode converters within the power supply. So we've got a few little things there that we can look at. So with this being a 2,000 page service manual, I now need to find the schematic diagram for pin number 1 to 14 on that connector, so we can look at the supplies more accurately and measure them on the DC meter. But as I said, there's no point going into, you know, all the system etc. and dealing with that until we've checked the power supply. So I'll just find the diagram and then we can continue on with that measurement. Okay, so we've got the diagram now of PLA, as we can see, with the different supply voltages etc. that are expected there. This is on the distribution breakout PCB, which we've got numerous supplies on here that we can see, but basically PLA is this connector here on the PCB. That is the feed-through pins from the power supply module that lay underneath, and then that distributes power to all these different sockets. So you're best off checking your supplies on here first and then progressing to the sockets themselves if you think there's a fault on this board. But yeah, so this is the supply line voltage measurements there. So there are some more sockets which is just off the other side of the board there, which is you know, PLG as well, which is this little black socket right at the end just there, and then the rest of them, as you can see. So what we'll do, we'll try and get in the picture then the multimeter at the same time. We're lucky with this power supply because its 0 volt reference line is to chassis, whereas on some test equipment it's isolated. Some supplies are isolated from chassis and some aren't, so you get a mixed bag, whereas on this test set the the 0 volt reference is straight to chassis. So we've got our multimeter neg probe connected there, and basically we're good to go. We can measure on pin number 1 now. I'm expecting on pin number 1, just trying to see if I can light this better. Okay, so on pin number 1, I can get a damn thing to focus on me. We should be getting -5 volts on pin number 1. So let's see what we get. So yeah, we're getting sort of -5 volts, more or less bang on. Pin number 2 should be, I think that's a +12 volts. Not far off, 11.28. So we're looking about what, a 0.6 of a volt, 0.7 volt off roughly. Nothing to worry about there. Pin number 3. What does it say about pin number 3? Oh, this is there won't be a supply on that unless you've got the battery connected. It's for battery option, because it says C note 3 for that, so we're not expecting a voltage on that. Pin number 4, that should be +32 volts. That powers the CRT display module. And then pin number 5 and pin number 6 are ground connections, and we can confirm that because we're only getting 23 millivolts of noise. And then the next pin, yep, same again. So then pin number 7 is the next one. Pin number 7 should be giving us, according to this, +5 volts. And the next one should be +5 volts as well, because the track's soldered to the same pins. Yeah, and then pin number 9 should be +12 volts. So we've gone to that. So 11.8, as close as it can be. Pin number 10 should be ground. So we'll connect that. Yeah, we're getting 25 millivolts of noise. And then pin number 11 should be -12 volts. And we are getting -12 volts. Pin number 12 will be 125 kHz signal for the power supply unit. So I'm not going to bother measuring that on this because we can't see it unless we're using the oscilloscope. And if that wasn't working, the power supply wouldn't be running. So then pin number 13 is the power down line, which comes from the microprocessor to the power supply. So I'm not expecting anything on that because this is pin number 13 there, 5 volts. It's just active high, that's all. Pin number 12, by the way, that carried 125 kHz signals floating about 2 volts. But anyway, pin number 13 is the power down line from the PSU, from the microcontroller, and that's held at 5, so that'll go low when it's wanting to power down. And then of course we've got a temperature control line from the power supply for over temperature, which is pin number 14, the final pin. So when the temperature is excessive, that line will be pulled down to ground, but it's active high at the moment, so that's a good sign, because it means the temperature of the power supply is good. So that looks all good. Now PLG down at the end here, this has got some power conditioning, we've got some series inductance, etc. And we can measure on these obviously, because these are the same supplies. Now PLG is one of the main supplies that go off to the RF assembly, so we should have all these power supplies on these. So for example there, -12 on this one, -5, +5, +12, and then 31 volts. So that's the main output, if you like. So that's all okay, but what we'll do is we'll go through the video anyway. We will continue to measure power supply as we go along, because sometimes they become erratic with temperature, and that's a known fault on these, but we'll keep coming back to the power supply throughout the video. But at least before we started delving into the main crux of it, we've actually measured the power supply, and that's what you should do. So now we're happy with that, we can progress on now to other measurements. Okay, so I've got it apart now. Before we look in this though, just want to have a look at I've got a spare front out of my parts bin here for a Tetra version, but sadly it's in different language, because as you can see here with these keys and the way the scutching's written, it's in a different language. So I use this for spare parts, the rubber buttons that are not in a different language, or the PCB tactile little dome contacts and things that's underneath. But we can get a fair bit of information about this faulty test set off the spare part here that we've saved. But yeah, it looks like as if the this connector at the top there controls the columns, because obviously we can see the tracks going off to the columns going down across the board, all the way across, and then this connector down here, which is immersed in all this black sooty stuff, that comes up and obviously does all the rows sideways along. So it could be some issue around this connector. It could be the test set's got wet at some point, particularly if it's been left outside in rain, or taken to a customer's site and rainwater's got in the front because it's been sat like that. Rainwater's got in maybe, and it's dried out and then started to corrode these contacts underneath. It could be that. Could be all sorts of different explanations as to why. But we do have a spare PCB here anyway if we need it, and I've got other fronts like this as well, lots of spare parts, so that'll help us. So yeah, but looking at the radio test set itself, obviously you've got the power module at the bottom, which is this big thick module here. That's quite difficult to get into regards the power supply, and there are videos coming up shortly on the channel about repairs in those. We've got the time base 10 MHz reference oscillator down here, which is the instruments what would be calibrated against another instrument for accuracy, frequency accuracy. Then here we've got the 3-volt battery for the memory backup, and then we have in a cassette just in this section here, these are system cards for the analog and digital functions of an instrument. So basically this cassette, you undo 2 screws down there and the whole cassette lifts up and out, a bit like what it does in Agilent spectrum analyzers, where it opens up like a book, and then under there are other system cards as well which you can get to. At the side here, this is the step attenuator for the receive signal generator just under the battery, this module here. That is where these two connectors are connected to. So basically it's very similar to the 2955, a Sig Gen input and then the output, and that then goes to this module up here, which is the RF attenuator, step attenuator section for what is the high powered input side. So that's like a 20-30 dB pad for the antenna N-type, if you like, as well as the TNC low power port. That's all dealt with in this box module, which we'll see more of when we look at the test set more in depth. This particular board here is a card reader board, and also does some audio switching and routing, as well as some RF functions that take place on there. Obviously we've got the monitor here, and with these holes allow us to adjust the monitor respectively. If you need to get the monitor out, it is actually quite a major strip down job. You have to take the front off the test set in order to get that module out, because it's pretty well impregnated into the instrument. And if I just put that to one side a second so we can turn it round, and then on this side we've got the RF tray here on the bottom. This is the main RF tray, however sandwiched in between this and the top section, because this is the bottom of the instrument, we have other RF modules which you can probably just about see sort of inside there, buried deep down, but there's another layer of RF boards and screening cans just on the inside in there, although it's quite difficult to see at this stage. Obviously that's a continuation on the board for the stability 10 meg time base, and this is a top part of the power supply. These power supplies were made here in the UK, and that's the company there that made those. Upstairs here we have what would be the continuation of the RF module there. Just down there you can see that's the main attenuator unit, which is quite a large box actually screwed to the side. Got the underside of the monitor there and all the connecting cables, and then right underneath under there we've also got potentiometers, etc. And yeah, so it's pretty well put together. I've noticed that screw there looks like it's out a bit. Yeah, it's fairly slack. So does that tell us a tale from previous? Somebody had a go at that. Somebody tried stripping the power supply down maybe, or getting into that, because that screw's loose as well. Both of these, or is it just heat, power up and heat cycles? I can't see anything else that's obvious at this stage. Just have a look. Now you can undo these screws here on either side, and when you've disconnected all the relevant plugs and things, this tray folds down to get access to the other boards as well. That does look like as if somebody's perhaps had a bit of a go there. I've just noticed that. The screw hole there looks like as if there's been something mashing up in there. Doesn't look too good, that. And that goes into the RF attenuator unit, which is, just to give you clarity on how deep it is, it's that deep is the RF attenuator unit, because this is the top section of it there, and this is where all your RF connections are made for input output, and then the other side there is just to there. So that's how deep it is. It's quite a thick, wide, long, deep module in there. But yeah, other than that, I mean, it's there's more to it than meets the eye. There's plenty more things down underneath in the middle as well. Okay, so you might just be able to see the connector there, the gold pins that are coming from the front, as you can see there, look. Now it's interesting that as I'm pressing on the escutcheon on the front, I can see the gold pins moving in and out as well, and that looks like it's loose a bit there anyway, that. But it could be a dodgy connection. So maybe if I push on there at the same time, it might get the connections to be made. Might be that it's moving the pins in and out. Who knows? But we can verify that. But yes, it does seem a bit strange. There is a finger connection down there for mechanical. I think it may be that's missing. There should be perhaps a screw in there that then goes through onto this mechanical thing behind to make sure that's pulled in, perhaps. Maybe that's missing, and maybe that's what's causing a dodgy connection. So we can power it up, but as you can see, the plug's definitely moving there into that socket. So yeah, we'll have a look at that. Right, so if I press in there and then press the help button, it's not as if a dome contacts needs a lot more force on it, you know. I'm not getting anything, but I'm pressing that in there and we're not getting any difference. So at least we've tried it, that's the main thing. But you never know, do you? You never know your luck. Obviously not that then. Okay, so A7 board, which is where the connector from the front panel connects to, that board we were just looking at with the plastic cover on it. That's this board, which is this entire front panel interface. Now we've got a couple of connections here for obviously rows and columns, which are these two here, and they're the two then that go off to the board. Now if you notice, there are two sockets, sort of socket A and socket B for the row and just socket A for the columns. So potentially it's that top and bottom connector, but I'll verify that on the service spare that we've got here. But basically, top and bottom of it, it talks about the keyboard scanning. And obviously it says the front panel keys are arranged in an 8 column by 9 row matrix. Row and column signals, row X and column X, are connected to ports 1, 3 and 4, each line being provided with a pull-up resistor. When a key is pressed, a row line is connected to a column, which is detected by the microcontroller. And then it goes on about all the other things like the variable control, the scope, position, squelch, etc. And it talks about that as well. So there's quite a bit on this board as well, not just for the keyboard but also the memory card, etc. That's all there. So yeah, I'll see what the front panel shows now. Okay, so we've got the keyboard layout here, and it references these switch numbers here, which then correlates obviously to the text on the front, and obviously the diagram which is here for all the different switches that I want to look at. Now one of the issues that I've had is trying to decipher which they are between S50s ranges and S60s, but looking at it, it looks like as if that's S52, switch 52, switch 51, switch 50, and then switch 57 there, and that's switch 56, and then switch 55. But I was just counting up, because what's strange about it is when you look, if I just zoom in, some of them look like 60s, you see. It's not until you zoom in a bit more that you lose the detail, obviously. So, and then your mind starts playing tricks on you. Like for example, to me, that looks like a 60 there, you see, and that looked like a 61. That definitely looks like it's, to me, a 67. Oh dear. You see, that is a switch 68, that, as well. But it's when you compare the both, you're trying to look at a 5 from what would be a 6, because the detail's quite bad on the manual. So I sort of like did a count up, and of course then I started thinking, well, where's these other switches gone? Because when you look here, for example, that switch 41 there on that right hand corner, then we jump from 42, then switch 43, 44, there's obviously switch 45, no idea where switch 46 is because I can't see that, but if anybody sees it, shout out. And that's switch 47, switch 48, then when we go over this side, there's obviously switch 49. Oh, that's where 46 is then. Switch 46 is there then. So it goes 45, 46, 47, switch 48, 49. So where's switch 50 then? This is switch 54, 59. And then that switch 50 there. That's it. Switch 51, 52, and then that must be switch 53, and so on. So it's how I sort of worked it out. But anyway, because sometimes the 6s look like 5s with the way the photocopy has been done. So I sort of drove myself mad, you know, trying to work out. And I thought when I saw that, I thought that was switch 66. But obviously we've got a switch 66 there, you see. So anyway, I suppose it depends how you zoom in, but it did look like a 60, that, because it was sort of joined, but it's got a bit of a flat top on there. So anyway, that looked like switch 61 to me because of this little leg thing coming down. That looked like a 6 rather than a 5, because a 5 sort of had a flat top like that, and that's got more of a bend in it. So I thought, oh, that must be switch 61, but it's not switch 61, because switch 61 is there. So it's not to compare it between other switches that you realise you've messed it up. But anyway, we've at least know what those are now. And so if we zoom back out again, if this bloody thing would do its job. We've obviously got the see if I can get on to the next diagram. We've got the LED for the power there, the supply LED, which is fed on a connector nearest it, which we'll have to have a look at this one, which is, that's the LED there for the supply. Where is it? Sorry, there, that's the supply LED, and that's the connector for it there. So we'll have to see if that's getting supply, because that LED wasn't coming on. And then the other switches are, so if we look at switch 52 and 57, switch 57 is the help menu button. So if we just zoom in a little bit here, just to see if we can see these switches a bit better, and what have you all. So right, 59, 50, where's switch 57 then? That's 58, 53, 40s. Switch 57 is that one then, so it's going up to, it's column 4. So switch 57 is column 4, and which would be pin number 14 on PLJ, Papa Lima Juliet. And if we go across, it's on PLK row 6, so it's PLK and it's row 6, and it is pin number 1 of PLK. So that's where we could measure to see whether when we depress that, that obviously that row and column connect together. Now it could be there's some corrosion around these switches, because you've got switch 57, which is a help menu button, you've got the frequency button decrement, which is 56, and then the level decrement button, which is 55. So it could be there's a broken connection somewhere here, along here, which is preventing these three switches. And likewise, the next row, which is switch 52, 51 and 50. Switch 52 is the AF analyzer menu. So switch 52, if I can find it, if my eyes don't deceive me. So I'm looking at it from about 2 feet away through a viewfinder on the camera. Switch 51, 52 there, look. So we've got switch 52, which is this one. That is the AF analyzer button. And we've also got switch 51 and 50. So these three again here are on that row. They're on row 6, same as the others. So that entire row, then row 6, affects all of them. So switch 52, 51, 50, 57, 56 and 55, that cluster of 6 buttons is all on the same row 6, but obviously on different columns. So it'd be interesting to see what's going on around pin 1 of PLK, and obviously pin 21, 22 and 19 of PLJ, and also obviously for the other 3 keys, which will be pin 8, 1 and 2. So we'll have to see whether we can measure that now by removing that board. So it's quite interesting. Let's see whether it's something basic. I'm just trying to avoid, in all possibility, removing the front cover from the radio test set, because it is actually quite an in-depth, laborious job. And if we just zoom back out again, so basically this board here, designation is A7. So this board is the board that deals with the memory card as well as the keyboard, and it's like a satellite controller to the main microprocessor board. So we've also got some other switching that's going on here. It does multiple functions, does this board as well. But we'll go into what this board does in more detail a bit later. My main thing is this connector that's up here. It's just hidden. This resistor network here is a pull-up resistors that's across all those switches on that side. So these pull-up resistors hold those lines up for the rows and the columns. So when you press the button, or it'll earth it on one side when you press the button, and obviously pull it down. So the idea is to remove this board. Now I'm hoping it's just a case of taking these 3 screws out and then removing it, but something tells me it will not be as simple as that. I can't see any other screws round here at the top end, and it does feel fairly stable there. So whether it's just holding those 3 screws, because the last thing I want, even to just get that board off, is to have to take the front off to measure, unless I can find the pins on the ICs that it connects to, which will be another thing I might have to do, rather than strip it down in order to get to that level of detail. So onwards and upwards. Okay, so as per the diagram, pin number 8 on socket A is for the column, for switch 57, which is a help menu button, and pin number 1 on socket B is for row 6, which is the other side to switch number 57. And the pin out goes, because pin 1 is in the bottom left, it goes 1, 2, 3, 4, 5, 6, 7, 8. So it's like up, down, up, down, up, down, up, down, etc. So that's pin number 8 there with the black probes connected on, and that's pin number 1 there. So when I press what is the help switch there, which is this one, we're getting the continuity on this test board of ours. This is a spare board. So I'm looking to try and duplicate that test now in the test set. The only problem is trying to get onto those pins is quite difficult because of the way that the socket sort of set back inside the case goes over it quite a bit. But I do have some special push on little probes that I've got here somewhere. I just need to find them, and I can just gently push them on, because you can't get them on at the side like on these while it's in the side of the test set. I don't want to risk having to try and push probes on from a multimeter and then trying to push the button at the front, because you can bend the pins slightly out of line, and that way we try and plug the board in, it can snap the pin off or bend it out of proportion. So we've got to be careful doing this and make sure that when we do it on the test set that it's done properly, otherwise we can cause a problem rather than try and find a fault. Anyway, I found out the reason why the LED is not coming on, because that was just rattling around behind there, and that's where that socket there that plugs in to the board, the front panel board, and obviously that connects to the LED. So it's actually on this board here. Just move that out of the way a second. So the LED is on the top corner, which is there. That's it, the LED. So that's not illuminating, but on the other side is this socket there. That's where that little plug that we just seen flapping around connects to. So that seems to me that somebody has definitely been having a go at this, and I had noticed as well that the SMA here, so the SMC connector here, got a little bit, some marks on it on the outer collar just there. So somebody might have been messing about with it. You can see there those score marks in it. So yeah, plus as well with that screw up here, nut and bolt thing that goes through to clamp when you press obviously the front in, that clamp is designed to clamp it so that front bit there, that bit doesn't move. So that was missing, in combined with the evidence on the side there with the, because this is the A7 board, that's the controller, if you like, the satellite control that's separate from the main logic board. So it's a card reader and the keyboard reader. That's socket A that goes to the multi-way connector on the front panel membrane we've just been looking at, and that's socket B, again goes to the front panel membrane. And then we had, of course, not forgetting this screw that was on the just there, that was all mashed up in there with the look of it, and that's missing. So I can now see that somebody's been into this before me. It's obvious that, yeah, we have had some little hands in it before, perhaps having a go at it and then perhaps giving up, maybe, I don't know, but makes you wonder, doesn't it? So anyway, we'll progress on to the next stage of trying to test that connector now. Okay, I've found out why we might be getting this problem in trying to look at these pins to go on to. Let's just see if we can zoom in. Not sure if you can see that. That's PLB, and the pin's bent over, so it's obviously that little end pin there. Now we might be able to straighten it up how it is, but that's obviously the reason why that won't work. And obviously I'll need to check these pins down here as well on that connector to make sure they're okay, but that's definitely got a bit of a dodgy pin on that. A couple of pins with the look of it. Oh, maybe just that one on the bottom left hand corner there. Hopefully we can straighten that up. I don't want to have to replace that socket, because it means having to take the front off, but we might be able to straighten it up while it's in situ and get that back working again. Interesting. Somebody's definitely had a go at this before me. Okay, so we straightened that pin out the best we could, and all looks a lot better now. I'll just gently push the circuit board back on and make sure that it mates properly, and then take it from there. They look okay. That's down there. If I can just get rid of that connector. All those pins there look okay. So yeah, it's just that side down there, that little connector. Anyway, it took some doing, I'll tell you, trying to get that straightened out, but we managed it. Just got to hope now it's aligned enough so that the circuit board socket lines up with it as well. So back soon. The socket on the board's not fared much better either. Let's have a look. You might have to just see the receptacle inside on the bottom right. Seems to be bent out of proportion. Let me just put this on and see whether we can get right into it. Just have a look here. Might be able to adjust the focus. You see inside there how it's bent, that receptacle. So we're going to have to shove something down there and try and open that back up again, because it's in such a bad way. Is that in comparison to the rest of them? Oh dear. Okay, so that looks better already on the right, ready to receive the pin. So much better. Give it a whirl, put it back in, see if it works. Okay, the moment of truth has arrived. We've reassembled it and put the A7 board back in now. Very carefully plugged it into the front assembly. We powered it up. We've got the LED back because I managed to get that connector plugged in on the rear, which was a difficult job to do because of the tight space involved. So the moment of truth has arrived, so if everybody can keep the fingers and toes crossed, and let's see whether these buttons work. So I'll hit the help menu first. It does, thank goodness. That works, no problem. We can get into user calibration now, which is what we need to get to. We'll just go back and just this next button, AF test, which gets us to the full function multimeter, or alternatively gets us to the audio input output test. So that's working. If I just go to RF Gen frequency, set up an increment of 100 megahertz. When I hit the frequency button, it's increasing and decreasing in frequency, as we can see there on the RF Gen as I'm pressing those buttons. So those two are now working, and those two RF Gen level 1 dB increment, oh sorry, 10 dB increment. Am I messing about? Yeah, there we are. And now if I press the up and down 10 dB, here we go. Look, does that when you press the right button? Right, so that's working as it should do. I'll just check that the rotary control still works as well, which it does. So that's okay. Right, so into the calibration menu now, and we will look to see what's on that. So if we press the help button again into what is user calibration, so user calibration. So the first option I want to run, just to try it out, is the run broadband power calibration. And what that does, it switches internally within the RF attenuator assembly for the type N socket here and the TNC. The module that sits behind there we're looking at earlier, which is that big silver block, and if we just turn it round, you've got a calibrator input coming in on one of the coaxial cables, and the calibrator switched in. The output level comes off one of the boards, which we'll look at soon, and the calibrator signal is fixed at 0 dBm, I think at 150 megahertz or 50 megahertz, something like that. It comes in and it gets switched into the path, the RF path, with an internal relay, and that then goes out then to the TX monitor when it's in calibrate mode to calibrate itself. So it's an inbuilt calibrator It's just like if you see the, I think it's the FSB 30 video, the Roden Schwartz FSB 30 spectrum analyzer. That does the same. That's got the internal calibrator within it. It switches it. Most equipment these days has external calibrator ports coming out, say a BNC or whatever, and you link it to the RF in with a little link cable. But these test sets, like some of the Roden Schwartz gear, use an internally switched by an RF relay. It does it all automatically, so you don't need to link anything externally. So what we'll do now, we'll just run the broadband power meter calibration on its own, and I just want to show that working first, so that's what we're on with now. It takes a few minutes for it to do it while it goes through all the different RF attenuator settings for the TX power attenuator, because not only is there a fixed 20 dB pad pi attenuator that sits behind the end plug, which is rated to 150 watts RF power, but beyond that there is also a relay switched attenuator which has various stages to attenuate the RF power coming from the 20 dB pad. And so what it does, it calibrates the power meter that is the next module on from the switched attenuator to different RF levels. So you'll hear the relays clicking in a moment, which will signify those changes, and then it should pass. It shouldn't come up with any fails or anything like that, so it'll be interesting. It could be that after the next step, when we plug in an RF source again to check the TX power, if the TX power is still off, it could be the calibrator itself isn't aligned properly and the RF output to the calibrator isn't at 0 dBm. So that's a relay step there, another relay step, and then it should complete its test in a moment. But if it doesn't read properly, then we might have to adjust the calibrator, or it could be a fault within the RF path somewhere as well, so that's always a possibility. But we're starting at basics, obviously. Run the self-cal, then check the power. If the power's reading okay, then we know we're just down to calibration. So anyway, it shouldn't be long now before it's done. Oh, it says it's done. There we are, look. I didn't see that, too busy talking. Right, so we can run all of them, but I just want to check the RF power now, and go to TX test, and then what we'll do, we'll put the transmitter source back on and let's check the TX power. Okay, so having gone through the calibration sequence, you can either do it through user calibration, but basically there is user calibration. Oh, I keep pressing the wrong button. User calibration, and then you can do the run broadband power test. So in there, what it will do the broadband power alignment. It only takes a few moments for it to do it. It puts on a 0 dBm signal internally and connects it, routes it through the RF relays back to itself. So it's using that as a reference, and that 0 dBm level can be adjusted as well, which I think is on the AE7 board, which is the interface card that sits at the top here, just behind. There's a little blue potentiometer that you can adjust the output of that board for 0 dBm. I think it uses 150 megahertz as a reference, or 50 megahertz. Can't remember now. It's in the manual. And then what happens is then you can follow in that calibration routine. You can then obviously measure TX power correctly, as long as that reference is set up properly, obviously, because if it's not 0 dBm and it's off, then what will happen there is that it'll align itself to a wrong reference level, and then naturally it'll not be able to read correctly. So that's what it's just doing now. Takes a few moments, that's all, for this broadband power thing, and then when it's done, that's it then, it's saved it automatically. So it says done there on the screen when you look at it, so we're good to go. So right, if I go to return, go back to the transmitter test, and now we queue up the transmitter, If you remember earlier, we had no power at all there, so let's just see whether that's restored things back to where it should be. And indeed it has. We're reading, you know, 4 watts there, so 4.7 watts. And just keep the transmitter, should find the frequency which it's doing as well. That's no problem. Right, just going to try it on VHF on 145.5 megahertz, and it's tuned into that frequency. Yeah, and it does the right amount of power, because this transmitter is definitely doing that power, because I've got it set to medium on here, so that's correct level of power, so I'm quite happy with that. So it just needed calibrating that. Obviously we couldn't get into that because these buttons weren't working. So now that we've done that, at least that's restored the TX power. I've still got a problem with the mod though, but that might be due to other things that we'll get into as we go through other tests. But yeah, we'll see where we get. Okay, so let's use the Rode and Schwartz test set to connect our TX power source to, and let's see what that works. So I can shift that Marconi out the way, and then connect our transmitter source up to the Rode and Schwartz. We're on TX counter there, we're okay, we're good to make a measurement now, so we'll just zoom in on the screen and let's have a look, see what power we get then. So we're getting about 5.1 watt roughly there. Okay, right, we'll remove that then and connect this then to the 2966 radio test set. So we'll just move that back over here, and then okay, so let's just move that into there, into that position. Okay, so we'll connect up the signal source now. Make sure everything's all done up nicely and tight as well. Okay, right, so let's go to transmitter test and then key up the transmitter, and then let's go in. So we're getting just over 5 watts there, 5.01 watts, so nothing wrong with that, but we'll check it against some more meters if we need to, but that's about right, nothing wrong with that. Obviously we need to do a full test now on the TNC as well, but we'll use a different power source for that. We'll need to check the RF gen, which I can do on this. Let's just get this radio to come back on, and then go to RX. We've already got the frequency set up. There we go. Nothing wrong with that. We might have dirty contacts in the, you can just hear there, look. Maybe not. We'll verify that on the spectrum analyzer. Right, turn the mod off. Let's just turn that round there, so it's this. So this module is the step attenuator for the SIG Gen. Now it seems quite solid. It did give the interpretation earlier that it was there's some noise there. It seems okay now. Yeah, can't get it to play up, but we'll keep an eye on that. Never know. That'll be one to test, I think, after it's had a bit of a cool down overnight, when it's all been switched off and gone back to room temperature and not being disturbed for a night, and then switch it back on again in the morning and check that. And I've had faults like that reappear when things have settled back to room temperature, because obviously this test set's been on a while and it's warming up now. You know, this feels quite warm in this area, so that'll be one to keep an eye on. But we'll do the RF verification checks anyway, and what we'll do, we'll check all the levels anyway now. So this is where we enter in the next stage of the calibration checks. Right, so just a bit on how to calibrate the instrument and what needs to be done in order to align the modules, including the spectrum analyzer, SIG Gen, power meter, etc. There are two areas of calibration on this particular instrument, so I'll just show you both of them. One is a user calibration and the other is a factory level calibration, which takes place using an ATE basic program which runs routines within the instrument, and it sets the instrument up in a particular way where it then stores DAC values that represent level and frequency for audio, RF, spectrum analyzer, SIG Gen, TX power meter and everything else in the instrument, and those values are stored as part of factory data within the unit. And obviously that is the deep level calibration which we need to do when, you know, we're doing the repairs on the instrument or alignments manually. We might need to run that again, so I'll show you both of them. Now, under the help setup menu, obviously we've got user calibration. So within the user calibration settings, there are base data which is stored there from factory, what is the deep level Marconi service data. That data is referenced to when making a calibration, and it does basic checks as part of this calibration routine. So it's not a full in-depth calibration, it's just a basic level calibration, and it will go through those steps using the data from the factory defaults that were selected, and then it will then check itself against those factory defaults. And so we can run all these different tests as highlighted here. Now, to get into the deep level factory Marconi service side of things, there's a hidden menu which only appears when you enter a secret code, and that menu appears about here, and I'm going to put the code in a moment so we get that Marconi service menu to appear. Now, once we get into that menu and put it up, it will then show many features in there like diagnostics, factory calibration data, load default data in there from factory, production values, things like that. So But what I'm decided to in this video is I've decided not to show that code, because anybody who faffs about with that code and gets into the secret menu will then be able to pretty much destroy a test set if you don't know what they're doing and they're not reading it in conjunction with the Marconi service manual. So what I'm going to do is I'm just going to move the camera away so we can't see what I'm typing in, and I'm now going to go and type in the code in order to allow us to see that. Okay, so now we've got the secret Marconi service menu which has appeared here. Okay, now then, when we go into this, then we've got various options that we can go into. So for example, we can go into cal values, and in there then we can calibrate the signal generator, the power meter, the spectrum analyzer, AB4 is a circuit board, and then obviously we've got audio generator, audio and DEMOD, scope, external modulation, AF multimeter, digital systems board, etc. So for example, if we went into signal generator, we can then select default data from manufacturer. We can go into cal config and set up then what we're going to calibrate, etc. And this is already in conjunction with the service manual, because there's prediction factors and things like that that are entered in. We can then start the calibration procedure by pressing the cal button. Once the cal's run, and it runs a basic program, and it starts doing its memory stack and going through all the parameters, when it's completed that alignment, you can then store the data. Now you can also recall data from either a previous store or a manufacturer store, and you can then set breakpoints as well, so that while it's doing the calibration routine, if it finds a fault where it can't calibrate itself, it'll stop the cal there, and it'll allow you then to do diagnostics to a deeper level. So that's that. Same with the power meter, very similar thing. You've got lots of different parameters that you can set up here, obviously, as you can see all the way down, and this is very important obviously for calibrating the RF power meter for the N as well as the TNC socket. And again, same procedure as before. You've got default data, you've got cal DAC offsets for things where you can't quite calibrate it precisely, you need to do minor manual adjustments. So all that's there as per the other bit. And same in the spectrum analyzer, again under cal config, and then you can basically run. These filters can be adjusted manually on the board. They're set at factory. Unless you replace a board, you shouldn't need to calibrate this anyway, but that option's there. Frequency response for the input filter, spectrum analyzer, cal points at 10 dB as well, and obviously a log amp linearity, and all these measurements can be done in there. In addition to that, there's obviously lots of other parameters there. Any warnings, there's none there because we've run this earlier. Now each one of these takes a long time to do, so the signal generator is about an hour to do, and the other two are about half an hour each, so that's 2 hours just doing those three. So that's why I've not videoed it and included it in this video, because it'd be too long otherwise. But it's just a program, it just runs it, that's all, and it either passes or fails at the end of it. It does, it searches for, sets up audio and RF signal levels within the instrument, providing they're being set up properly manually first, and then it uses those as a calibration standard in order to calibrate itself, and then it stores the data into its own memory for recall later when we then do the user cal, which I showed you earlier. As well as that, we've got diagnostics menu, so in there we've got lots of different boards and modules we can go into. The memory mapping, and obviously we can look at the RAM and the E² PROM. We can go into the attenuators for the step attenuators and manually switch those in and out as we see fit to do tests of that. There's all sorts of different things as well, like we can go into like the different boards and modules and set up different things and do diagnostics within that and corrections. We've also got debugging as well if you want to do that, and then I think there's boot options as well in one of these menus here. Here we are, look, pre-boot options, so you can run main code, reboot mode, test the comms of the communication port, GPIB, etc. We've also got production values as well from Marconi, where you can load those in for a calibration. You can clear the memory if you want as well, so that's these here. There's a CRT test you can go into and arrange different tests in there. There's lots of different things that you can go into, and that's just in that one diagnostics. Now when we go into the Marconi service menu as well, there is a counter up here. So if, for example, you power cycled the test set again, that Marconi menu will appear again for up to 10 times, and this will count down every time the test set's power cycled till it gets to 0, in which case then this will disappear. So obviously you can clear that yourself, and that's what we're going to do now, because we've done the calibrations earlier. We've saved the data into memory, we've restarted the instrument, and now we're ready to do RF tests. So I'll click address clear, and that's set it to 0, and now when I do return, you'll see that secret menu has now disappeared. And that means then of course we could go to user calibration and run, say, the digital power meter cal or any of the other cals. Obviously if those cals fail, then there's obviously a fault within the instrument as well. So, and some of these cals may not work, for example on boards which are not fitted, like say the digital systems board. So you can go into the cal setup, and often options that aren't fitted, those will be switched off, and all the other options that are fitted are on. So now we're ready to do some RF measurements now to check the calibration is correct against our bench equipment here. So we're going to use the Rode and Schwartz test sets, and we're going to use then the HP spectrum analyzer, and I'll just set these measurements up and then we'll come back and do some tests. Just one other thing as well before I forget is, when you've enabled the Marconi service mode here, under user calibration you get an additional calibration menu appears here, which doesn't normally appear unless the Marconi service mode's enabled, and it's for run DEMOD noise calibration. Now that is just under the normal user calibration menu. It appears as an extra thing, because if we clear the Marconi counter and come back out, so that's vanished, when you go into user calibration that menu disappears as well. So that's just one extra thing that you need to look out for. Okay, so we set up a measurement now at 456 megahertz. I've set up an RF gen level of minus 50 dBm, and I've just checked the spectrum analyzer, all connected up with the lead and everything. There's no modulation on because I don't want that, and there we are. So if we zoom in on the screen, you can see there in the top right hand corner we're getting minus 50 dBm. Now I'll start to adjust the up and down the RF signal, as we can see, going down into the noise floor and then all the way back up again as well, right the way up. So for example that's minus 40 dBm. I'll put in another level as well. Let's have a look at that one. That's minus 47 dBm, and I'll just go just at random as well now, minus 32 dBm. Just adjust it to that's minus 23 dBm. It's reading minus 22.98 there on the spectrum analyzer. So that's a little example of that. Obviously when we're doing calibration of these types of instruments, not only would we use the spectrum analyzer, but we'd use the scaler probes, because we're measuring the power direct on the port, whereas currently we've got a RF cable going for 0.5 meter to the spectrum analyzer. which will have losses only minuscule because this is aerospace defence grade cable from WL Gore, and its frequency characteristics are low loss right up to 18 gigahertz, but still connectors, RF adapters, plugs, things like that all have slight attenuation, even if they're gold plated like these. So you tend to make direct measurements using these for most of the dynamic range. In addition to that, we'll now have a look at the spectrum analyzer in the instrument and the TX side. So we'll just go to look at the levels there, because we did do a calibration on the spectrum analyzer as well as the TX power meter. So we'll just go into the spectrum analyzer there, which we've minimized it just for the time being. We're going to put a test frequency of 100 megahertz, and now we're just going to set up the Rode and Schwartz test set now in order to deliver that and connect it up. Now I've selected a level there, and if I can just move this camera in such a way I can get to it. Neg 50 dBm thereabouts. So I'll just plug that connector up there. If I can get these threads on this end out to bite. Right, so let's come back down. Okay, so right then, so we'll just switch the N on. Let's see now. Just need to go to expand. Before I go to expand, I've set the TX frequency to 100 megahertz and put manual tune, TX tune to off. So basically it will reference the frequency we put in and give us an offset frequency to check the internal time base of the Marconi. Now this Marconi is on its own internal time base, whereas my Rode and Schwartz test set is calibrated to an atomic frequency standard, which is here in the workshop, cesium rubidium clock. So that is very good, 18 hertz off frequency. I'm not even going to try adjusting it, it's spot on is that, you know, I'm not going to worry about that. It's well within spec. Okay, so now we're going to check the spectrum analyzer functions as it should do. So we're going to go to expand. It's important we check the levels of the spectrum analyzer. I've selected the markers on already, and we've then got the RF gen level, if you like, markers, and then let's have a look here. So we're currently outputting minus 50 dBm on the Rode and Schwartz, and we're getting a roughly about minus 52 there. Now I might be able to minus 51, flashing 52, so just a very slight loss there with the cables and connectors, so that's reading very well. I'm quite happy with that. I'm not worried about that at all. I'm quite satisfied. We can obviously do as near zero span as we want on that. I'm not providing any modulation either from the Rode and Schwartz test set, because I don't want any instability in that. Obviously this instrument's got a track gen on it, so I'm going to check that out as well a bit later as part of the alignments, and so I'm happy with that. I don't see an issue at all there with that spectrum analyzer. I think the calibration sequence is completed very well, so there's no issues there. What I will do now is switch the port to the TNC, and I do have here somewhere, you can find it in our little box of tricks, a TNC adapter, which I will connect to. If I can find the damn thing. Yeah, I've got it. Right, so I'll plug this TNC adapter on, and then we can connect the SMA from the N, which is connected on this cable here. That's if I can get it off, because I use like little spanners in order to tighten these damn things on. So let's see if I can get that off. It's proving more difficult than I thought it would do, as typical when you're videoing. You know, nothing's ever straightforward, is it? So let's have a look. So what I'll do is I'll just push that on for the time being, because I just can't be bothered faffing about on video trying to get that bloody SMA off there, because it's on really tight. So we'll just push it on lightly. Okay then, so let's have a look at the measurement. What are we getting then on the, again, accurate measurement there, minus 51 dBm, and obviously the reference signal we're pushing out from the rodent swatch is minus 50, so that's okay, well within spec. I'm not worried about that at all, based on the cable losses, etc. So yeah, very happy with that. I can expand off. The frequency area is correct. It'll auto tune as well if I turn the RF gen level up. In order for the test set to auto tune, it needs to have a high, relatively high RF level, because there's an area where it will detect a signal and then auto tune to it. So roughly about there. So as we can see, you know, if you withdraw the RF connector, you can do auto tune on, and then it'll search obviously for TX tune is on or TX tune is off, and it'll find it. Now the tuning only works within certain RF power level ranges, unless of course using look and listen or the off-air monitor feature, in which case it'll find the frequency automatically. But the frequency counter on these does need, I wouldn't say a fair amount of power, but it needs a few milliwatts of power in order for it to, you know, to lock on. So naturally, let's have a look here. So there we are. Look. That's an example. So TX tune is on at the moment, and so if I remove the RF signal, obviously we go to 0 Hertz, and when I then connect the RF signal, it'll auto tune then to that frequency, and it'll come up, which it's done there. So it's just an example of that test as well. So we'll proceed with some more tests, and we'll do some checks on the rest of it. Right, so I've got connected up now the external antenna cable to the antenna on the mast outside. So that's plugged in on the TNC. We'll just select the TNC. We'll then go to TX monitor. Just want to check that it receives a broadcast, demodulates a broadcast properly. It's fixed for a TX test, off-air test. And then we'll put in a frequency in a moment. I'll put in TX frequency, I can't remember what the, we'll try 101.1 megahertz, which is classic FM. There we are, look. And we can go to spectrum analyzer and look at the radio band that we're in, and then select obviously expand, and then we can go to tune to different frequencies. So you can only listen to them outside the expand mode, and then it'll do that, or we can just go to TX normal, look and listen. I think 93.7 megahertz. Can't remember now. What have I done there? I've typed it wrong. Frequency 93.7 megahertz. There we are. Look. And then off-air test. Right. Display gen. So you can see there, you can listen to off-air radio signals, and if you go back to scope bar, you'll be able to hear it.
He uses the Secret Service and microphones to eavesdrop on his competitors like Churchill. He's completely not the person
that works okay.
Understood him to be. He's
By
made
the
the
way, you're turning the story upside down.
Well, as a Churchill turned it upside down.
Adjust the
another
filters.
fact that I thought was interesting was Churchill. I approached this with great awe and respect and discover that he's been absolutely the architect of one of the worst military defeats to Crimea, and certainly since the Normandy.
So, that's a little rundown of that.
First question for you.
Okay, so now we're going to do an absolute measurement check now of the RF signal generator's output. So we've got the scaler probe connected here to the end port. This is obviously connected to the Marconi microwave test set, and we've done a calibration procedure of calibrating this along with its linearity and cal factor table that's printed on it, inputted that into the Marconi, and then done a power reference cal for this. So it's currently aligned to the room temperature of the workshop, and also the linearity and cal factor data's in there, and that's all past its calibration routine. So we're able to test measurements now. Now it might be that if a temperature changes here in the workshop, we'll get a message come up at the bottom which is prompting us for another cal if a temperature changes wildly, but I think we've got more or less a stable temperature in here, but you might see a message pop up. Hopefully not, but we've got minus 20 dBm. I've set up a frequency of 50 megahertz with a 50 megahertz increment. So when I press the up and down increment buttons here, it should obviously increment decrement the frequency. We'll leave a level where it is. I'm just going to check that we get nearly or spot on to minus 20 dBm as we possibly can. So I'm just going to check it now at 100 megahertz, 150, 200 megahertz, 250, 300 megahertz, 350, obviously 400 megahertz. More or less about what it takes time to settle the measurement sometimes as well, depending if there's a little bit of discrepancy. So already we're looking about 0.85 of a dB away from minus 20 there, and then we're looking at 450 and then 500 megahertz and so on and so forth. So we can keep doing that measurement right up to 1 gigahertz if we want to. But as you can see there, the level is is more or less spot on there without a problem, so I'm not going to worry about that, to be honest with you. It's very accurate. So that's just a little rundown of that test. Now we need to do modulation checks on both transmit receive as per standard alignments and audio checks and signaling standards. So this is an extract really of the audio cal that I'm just going through right now, which has now been running for 35 minutes. So it's just to give you an idea of what the test set's doing on a cal routine. This one is for the audio generator and DEMOD, or the audio DEMOD circuits for AM FM phase mod, and obviously the audio AF in analyzer, because this test set also has an audio analyzer, like a spectrum analyzer but for audio obviously. So it's just going through that now, and it's been doing it for the past 35 minutes. So yeah, it's running through various sequences as part of this. It's quite interesting to follow it, but ultimately we'll get to the end. It's set to break on fail at the moment, so if there's any fails it'll stop, but so far so good. So that's a little rundown of that. Okay, so where we're at now then, we're just going to do some transmitter measurements now on the radio test set. Obviously we've set up, in this particular case, the Roden Schwartz to generate a 100 megahertz at 1 kilohertz tone at 60% modulation. We're testing AM amplitude modulation now. It's always worth knowing, by the way, when you set up your SIG Gen on radio test sets, that if you set the SIG Gen to maximum output level, you're not going to be able to modulate the amplitude and modulate the carrier, because the test set's obviously producing its maximum permissible RF output. So you must always reduce the SIG Gen by at least 50% of its maximum, so that you can get up to 50% mod on top. And obviously the more you reduce it, the more modulation depth it can go to. For example, if the radio test set's only capable of doing 0 dBm output maximum from the RF socket, if you set that to 0 dBm and then expect it to modulate it at 60%, it's not going to do it, because you've already reached the maximum, you know. So you've got to have the RF signal level low, and then it can modulate the amplitude of the RF carrier power up to whichever you set it to. So if it's 100% modulation, for example, the ceiling, the power has got to be within the dynamic range of the signal generator. So, you know, you can't start with the maximum signal level of the test set and then expect to try and amplitude modulate it. So you've got to have this RF level low enough below the maximum level of the test set in order to get that headroom to amplitude modulate the carrier and get that AM envelope, that mod there. So, you know, you've got to be aware of that. Otherwise, you know, I've seen that happen a lot of mistakes where people have set up the SIG Gen to maximum output level just so that they can get the test set to be sensitive enough to receive it, and then they can't measure the AM depth, because obviously the AM depth is not achievable because the signal level's at the maximum of the signal generator. So reduce the signal level of the SIG Gen right down, so that you're going to get that headroom of RF power for the modulation depth. Now we're testing this at 1 kHz tone at 60% mod depth on amplitude modulation, and as you can see there, we're getting a reading of 60%. And if we look very carefully at the oscilloscope, just to check the ranging is correct, we're on 10% per division. So you might be able to just see the little green lines in there if I can get the camera orientated correctly. So we've got like 10, 20, 30, 40, 50, 60%. So that's reading correctly. And obviously if I reduced it to 5% per division, it'd be over modding. And then obviously at 20% per division, we've obviously got, if I can just move that up a little bit with the range, 20, 40, 60, 60% mod, etc. So I'm very happy with that. That's reading okay. Obviously the bar charts are there as well, so there's nothing wrong with that. So I now need to change the mod type now to FM, and we've got phase mod there and we've got FM. So I'm on FM deviation now, plus or minus 4 kHz deviation. So now I just need to set up this Roden Schwartz test set to now send FM. So we'll do 3 kHz deviation, and I can do it properly. 3 kHz, there we go. Right. And I need to change the mod frequency back to 1 kHz because I accidentally changed it to 3 kHz. Okay, so we're now generating a 1 kHz tone at 3 kHz frequency modulation, and there's already a problem I can see now on here, which we'll need to find out what's causing this. Obviously that's at 2 kHz plus or minus, so if that was correct, then the 3 kHz mod would be over modding the scope, and it isn't. So we'll just go to bar charts a second. So we're only getting 300 Hz deviation when there's actually 3 kHz being sent. We've got a speech band filter there set up for 3.4 kHz. I'm just going between the different IF ranges on the test set, and it's not making any difference to the mod, so it's not like it's an IF fault for narrowband, wideband, FM, etc. so that's okay. The bandpass filter there, 300 Hz to 3.4 kHz, that's okay. 55 kHz. Low pass filter, still reading 300 Hz deviation. No filter at all, 600. So that's interesting, is that? Yeah, there's something wrong there. Let's go back to the oscilloscope and just check the ranging. So if I go to 4 kHz deviation, it should be reading roughly right up to there, and it isn't. 8 kHz, obviously nothing very much. Oh, hang on, what's this? I'll just put that speech band filter on. Ah, now then, that's strange, isn't it? So it's saying it's doing over 20 kHz deviation, and I can just see there, look, 29.9 kHz deviation. Well, that's clearly a lie. 40 kHz deviation, it's doing 29.9 kHz deviation, 80 kHz maximum there, still 29. That's interesting. So if that's 40 kHz per division, or plus or minus 40 kHz, so yeah, that's 10, 20, 30, 40. So the scope doesn't read in reference to the level. The bar charts then, what are they reading? 29.8 and 29.8. So the same as that. We've got max hold on off, reset. So there's something strange going off there with the FM DEMOD. Now the AM works, obviously, so what's causing this then? Now we've already run the secret cal menu in there, the scope and FFT calibrations, and they passed okay. So if I just go up to here and let's have a look here, just need to input that code again just to check. Right, so if I go to there and then do right, so back to this again. So if I go into the Marconi service menu, and then I think it's under cal values, and there is a scope and FFT calibration, and in there then you can set up your cal config. So we can obviously do your all there on, okay, which is fine. Breakpoint was set to fail, and it didn't fail anything. I stored the date, and I've run this cal a few times actually. So we've got the demodulation, FFT offset, AF FFT offset, and then DC mark annulling or whatever. So that's all part of it. Audio and DEMOD, and then in DEMOD under cal config, we've obviously got the AF range on, the AF gain, AF filters, we've got the ADC, we've got the DEMOD noise. I set that to 1 last time, and DEMOD filters, peak detect. So these are for setting up the audio filters and the DEMOD. So I ran that and that all passed. There was no failures at all, because warnings is none. So that's interesting. So yeah, quite interesting is that. I just have to go back now and see why that's not working. So is it a scope ranging issue, or is it the FM DEMOD? So looking at this block diagram, we've got the AE7 board, which is a DEMOD board, and we'll have a look at that next, I think, because obviously there could be a fault on this board somewhere, so we'll just have to have a look at that and see what what it says, but I think we'll get the bottom of the test set off now, and we'll have a look at this board and where it is, and go from there. Okay, so we've now removed the bottom of the radio test set. We've got a giant screening can here, which goes over this. So I've removed that 1,000 screws later. Now, just to show you what's inside the instrument, it's still on at the moment. So basically, a little rundown of the boards here. So the board we're wanting to look at is AE7, which is this board here. That is the AM, FM and phase mod and SSB demodulator board. This green board piggybacked here is AE8, and this is the SSB option board. That's what's plugged in there when you buy the SSB option, is this board. Now we have the next board on here, which is AE6. This is one of the spectrum analyzer boards, one of two boards for the spectrum analyzer, and we've got the crystal filters here for calibrating the spectrum analyzer filtering. That's there. The next board along to the right here, this board here, is AE5, and that is the second and third local oscillator board. And the board beneath it, which is this board here, this board, that's board AE2, and AE2 is a first local oscillator board. And this board here is AE3, and AE3 is a first mixer board. And this board here is AE4, and AE4 is the IF board. Now if we look at the architecture in general, it's very similar to what's used in the Marconi 2955, which I'm going to explain in a second. But before I forget, I'll just mention this board as well, which is AE1. Now AE1 is the I2C bus data control board, and that is where the calibration data for most of these modules is held. So this is where the software control for the DACs to these boards are all controlled in this board here, and that interfaces to these boards to control various analog and digital levels. Now it's very similar to the Marconi 2955 insofar as this module is concerned in this area here, because this is the mixer board here, and what we've got essentially two local oscillators, VCOs. So for frequencies below a certain level, we've got essentially a local oscillator, fixed frequency oscillator here, like we have in the Marconi 2955, which mixes with a signal on this little copper contact there, coming from this local oscillator board. This is a mixer, and then that signal goes through this surface acoustic wave filter, this SAW filter, into what is the input mixer here. And likewise there's a second local oscillator which produces another signal on this contact into this board and mixes again. So for frequencies above a certain frequency, this local oscillator goes directly into there and then is mixed with a signal coming from here to produce the RF output, which obviously is further attenuated by two teledyne RF relays and a pi attenuator before it's fed out to the output socket here, before it goes off for final amplification, and then passing out obviously through the power attenuator, the pi RF pad to the front sockets, but also the step attenuators in between there as well, the mechanical step attenuator. So it's very similar in so far as when frequencies below a certain range are required, it uses mixing by a local oscillator feeding into this mixer, which is the VCO, variable controlled oscillator. Frequency can shift and change, and then we've got a fixed frequency oscillator here which produces a frequency constantly into this mixer. The two mix, and the difference between them is an IF which is passed through here, and there is a series of up conversion and down conversion that takes place. which we can look at later in greater detail. So that's, if you like, the RF Sig Gen local oscillator section, whereas this board on this side is the what was denoted in the manual as the receiver. The transmit monitor side, if you like, is called the receiver in the radio test set. Now, because there's other people's hands being inside this, there's a couple of little holes, and I've been reading the service manual, so when that's on there like that, we've got a couple of holes, these two here, which are for adjusting the FM gain and AM gain, etc. And then to get to further adjustments, then you have to remove a cam. And it could be that somebody's been fiddling with these potentiometers. Obviously it's that potentiometer and this one, which are the potentiometers that as part of the alignment procedure. So it potentially could be that. Basically there's a 10.7 megahertz IF enters the board, and then it uses that 10.7 megahertz to either discriminate FM phase modulation or demodulate AM, detect AM, and then obviously SSB. SSB crystal filters are placed in these three normally. I believe that according to the technical description in the service manual, AE8 is also used for digital systems. Not only is it an SSB board, it's also used for digital systems because of the Gaussian shift keying, the GMSK modulation content that's used in GSM testing. So it uses that board on 2966A and 2968 models only. That board is fitted. Other models you can pay to have it fitted, but I think if you do pay for the SSB DEMOD, I think you also have a free crystal filters added, which are for the SSB, which we'll see on the circuit diagram shortly. Now at the top here we've got various signals being fed in and out, and we've got voltages, so we've got like -12, +12, 5 volts, all that malarkey. They're coming in on these various feed throughs, so we'll have to check those as well to make sure, start at basics, that we're actually getting supply voltages to this board as we should be. I've just been looking at these electrolytic capacitors, and they don't look like as if there have been any leakages or anything. In particular these types of surface mount electrolytics, which there aren't so many on this board I can see, well, I can't see any actually. They're common for leaking, and then you get some residue around them and corrosion on the board, and I can't see that anywhere. I've just had a quick eye of it. So it's not like I've got leaky caps or anything like that potentially. I can't see any burnouts or damage here. There's no physical sign that somebody's been in, apart from there's a big nasty scratch on this screening can. So whether they've had this can off, which I think they have done, because when I did take the can off initially, I found this coaxial cable here, this, that had been pinched. It was sort of like that, and it had pinched it against this screening can, and I don't know if you can see that if I zoom in, although I have measured it off camera and it is actually working fine. You can see there's just a little mark in it there where my fingernail is. You can just see it there. It's a lot better now. It's puffed up a lot more now that a few hours have passed since I've had the screening can off. It's not as crushed, but that was crushed. Now the socket itself here, I've tested the in and out of the coaxial cable to see if it's short circuit. It wasn't, and this coaxial cable then goes down and solders the braid to this and the inner to that, and there's continuity between there and there in the inner of the coax, so it's not like it's open circuit either. But somebody's had this screening can off. For that to have been damaged like that and just left, you know, sort of flapping about in the breeze, is a sure sign to me that somebody's been into this level before. So if that's the case, and now it's nicely tucked away safely, have they been tinkering with these potentiometers? Anyway, basically what happens is the AE7 board, which is a demodulator board here for AM, FM and SSB and phase mod, that outputs its signal to another board. Now the other board outputs to A3, so basically PLE, which is this socket here, this is the FM DEMOD output on this coaxial cable here. That goes off then via the top of this off to another board called A3 rather. Now A3 is the scope board, and that's the board which then switches between AF inputs, AM, phase mod, FM, SSB, and it basically switches those in and out so that it can read what's coming from those various modules and boards and outputs. So there's a couple of adjustments we can do on this. There's a mod meter adjustment, which means having to adjust these potentiometers, and there's an AM and FM absolute accuracy adjustment as well. So it may be we'll have to resort to doing that, but I'm very reluctant to adjust any potentiometers at the moment because I don't know if somebody else has done that, and I'm not sure whether, if they've been set up at factory, I don't want to start adjusting them if I find out there's a fault on the next board on, so to speak. But there's certainly a lot of help in the manual anyway, and I'm sure we can work through it and get to that stage. Now then, let's put the screening can away. So if I move a tester out of the way a second and we have a look at the board here, as we can see we've got the 10.7 megahertz signal coming in, what is from AE5. Now AE5, as we described earlier, is the second and third local oscillator board. So AE5 has an output from that, and sorry, AE6, when I get my facts right, does help if I can actually get my facts right, doesn't it? AE6 is the spectrum analyzer board. So the spectrum analyzer board has like a pass-through to this board at 10.7 megahertz wideband IF. There's also a narrow band 10.7, so it basically bypasses a lot of filtering and comes in here. So that comes in and is then switched through a range switch here. So we can basically, we get this control from the I2 bus software control, which switches these ranges in. So when we want different filters in, then it'll switch these bandpass filters in and out, etc. And then obviously then move on, which then comes down to here. So it gets amplified. There's another mix here, 10 megahertz mixer, mixes with a 10.7 to produce 700 kilohertz signal output, which comes back this way and then comes into IC11 mixer. And we've also got another software control here, which then switches between sort of the discriminator and the limiter, or in this way. We've got some more amplification and buffering going on for AM. So for basically that's the AM path there. The FM path is via this limiter, and then the FM discriminator. We've obviously got a filter, low pass filter, because the upper component's cut off, and we've also got an FM offset correction here, and then we've got FM ranging. Again, the I2 bus data bus controls the FM ranging and the low FM low gain switching. So it'd be interesting to see if that sort of interacts with that. Now it then has a DEMOD output of FM, so the demodulated audio is then fed out on this PLE, which is that connector I showed you at the top of the board. Oh, we've got SSB here as well, look, so we've got basically AM, FM and then SSB as well, and there'll be a connection out to AE8 somewhere, so that'll obviously be the option, AGC signals, etc. So we've got DEMOD AM, which is working fine, however the DEMOD FM isn't. So yeah, is it a fault on this board in this area? I'm not sure. Could be a supply voltage issue or something like that maybe. I'm not sure, but anyway, so the I2C control sheet, AE1 I2C bus is decoded by IC1 to provide SSB on selection, AGC fast, FM low gain selection to set FM demodulation, wideband SA spectrum analyzer filter select and selection of required 7R 3.7 and 1 point crystal filter. These are not normally fitted. Right. So that's these filters here then that it's referring to, which are not normally fitted. So they're probably options. So crystal filters, AGC attenuator, mixer. Yeah, so it talks about that. 700 kHz past to AMD modulator, FM channel, the output limiter, IC9 differential square wave, V signals amplified by these two transistors, resulting differential signal at the junction representing the deviation of the FM carrier. It talks about these inductors and capacitors form a low pass filter to remove a 700 kHz and 1.4 MHz content, because obviously 2 7s are 14, which is 1.4 MHz for the second or the first harmonic. The R145 provided frequency response adjustment, and then it says the IC12 sheet 3 of the associated components forms adjustable offset voltage source for amplifier IC10. Normal stroke FM low gain control is provided by a switch IC18, which also provides the means of connecting the squelch signal from the A2 board. Gain may be ×1 or ×10, as referenced to in the section on AF DEMOD and multimeter ranging. SSB, so it talks about that, SSB digital signal board. So it uses again the SSB AE8 board for the digital systems. So that's obviously there, circuit description. So if we look at the circuit diagram next for the AE7 board, I think that might give us some idea. Right, so we've got the schematic diagram now of AE7, and if I just zoom in a bit, get this bloody thing to zoom in. Right, so I'd like to check the supplies coming in on those feed-through capacitors on the top. So we've got plus 12, we've got minus and plus 5 volts there, again minus 12 volts, another plus 12, minus 12, plus 5, minus 5, and all that fiasco. We've also got, I've noticed there, a little voltage regulator, an LM317L, a small little package device with 2 resistors set. It's a just leg to give a 9 volt output there. And I'm just looking here, we've got the SSB crystal filters, plus 12 volts to them obviously, and they're those 3 filters which are not normally fitted, it says. These 3, which are obviously that the thing on the circuit board we were just looking at. We've got an input switch there, so that's the wideband IF 10.7 megs coming in via this capacitor, goes to this ranging switch. That there looks like it could be the FM AM path, because that's obviously for one, that's part of the SSB, those 3 there, these 3 filters. So we'll go on to the next diagram. That's the I2C control. So we've got FM low gain there, AGC fast, SSB on. So that's the selection, if you like. Narrow band 10.7 MHz signal coming in there. And then if we go to the next one, again that's the continuation of the SSBs. And then we have that line that connects straight through. Again, another switch, which is controlled by that data bus there. And then the output of that is fed to here. And that's the AGC attenuator. Goes through obviously. And we have, with a look of it there, some kind of switching going on. So it looks like as if this is the output then. That's an IF gain potentiometer, runs off 12 volts, and this IC here is a RF amplifier, and then we have effectively two outputs from it. So if we go to the next sheet, where are we? Where's the discriminator then? AE7, it might be further down then. Let's have a look. That's AE7 component layout. Here we are, look. Right. 700 kHz BFO, so that looks like it's a limiter. Oh, there's some FM discriminator bit there, look. So we've got a 9 volt supply there, and we've also got a 12 volt for the limiter. What's this here? We've got a mixer thing going on there with the look of it. 700 kHz IF, yeah. That's okay, I understand that. SSB AGC, we're not bothered about that because it's not got SSB sort of enabled. Here we are, discriminator. So this is the FM discriminator. Right, so this runs off a 9 volt rail, which is off that 9 volt regulator. They're the two transistors we read about earlier, and then coming out there, because this ring mixer sort of thing here, ring discriminator, and these two transistors split off from the 700 kHz the FM frequency deviation, and this is running off a plus 9 volt and a minus 12 volt rail. There's another plus 9 volts there, look. So it's really important to check that 9 volt regulator, I think. And we've got plus 12 volts there. Looks like we've got some Zeners that clamp it, which are these two. So the FM DEMOD is coming out here onto TP4, and then we've got a potentiometer called FM frequency response. We've got some filtering, obviously, which removes that 700 kHz signal, and then we're going straight out there onto the FM, which is what we're picking up on that socket. SSB AM DEMOD, again potentiometer there and AM out, and we've got some other pots as well. I think I saw one for FM gain as well somewhere, unless my eyes deceive me. There's definitely one there for FM frequency response. I think there's one for FM gain somewhere as well. I'm sure I've seen something for FM gain. I could be wrong. This is a couple of potentiometers knocking about here. Anyway, we'll find it. FM frequency response. There's one called FM gain somewhere. Anyway, SSB demodulator, center channel offset adjust, FM offset correction. So that's it. There's two potentiometers for that then. One for the actual audio frequency response and the other center frequency. So this will set the 700 kHz up. And what else have we got? FM range, and here we are, look. Right. So we've got the FM coming in here, DEMOD. There's an FM gain adjust potentiometer. That's it. Then we've got a low gain and a set squelch to obviously switch the audio on and off. And then it goes to the final output amplifier before it then disappears off to the PLE, this socket. So that's that. Again, these are running off 12 volts. So that's a 9 volt there, look. We're clamped by a Zener, and then through this potentiometer here, which it doesn't tell you what that potentiometer does, but it's obviously quite critical because it'll set up the non-inverted input to this. So yeah, it's looking a bit clearer now. That's AE8 board. That's a printout for that, and that's the that's another board that's separate to this. Okay, so yeah, now when we get onto the other sheet, which is where we get the next board on, which is which it outputs then from AE7 to AE6, I think it is. That board then does the is it AE6? Can't remember now where it demods. Oh, it outputs to A3 board, which is the scope board. And as we can see here, this is the range switch here. So we've got things like, for example, AF, we've got power readings as well, and then we've got FM coming in, and interestingly enough we've got a cal signal here, look, which we'll have to look at this. There's a cal signal comes in. So obviously when it does its self-cal as part of that routine we were looking at earlier, it'll input an audio signal here into this range switch, and then it'll calibrate itself using that standard. So if this calibration standard's off, then obviously it's going to cause issues with the scope ranging. So we'll have to check the AF part of the scope works now, seeing as we found the RF side's a bit dicky on FM. That'll rule out if it's the DEMOD board, the FM signal coming in here that's the issue, or some component around it. Because if it works fine on the oscilloscope, because we proved it works fine the oscilloscope on AM, we just need to check now the audio works, because the audio signals are fed in here on the AF input selector switch here, and if that works then we know the scope board's fine. It must be the AE7 board which is faulty. Let's have a look here. Again, we've got an AF input from the front panel, so the BNC on the front of a test set is fed in there. And what else have we got? That goes through. Looks like there's some switching up to this cal line. So the calibrate signal also gets switched through here and then fed that way. So it can calibrate both the input ranging for what is the rest of the instrument, plus then calibrate the signal that's coming in from what will be measured at the front of the instrument on the BNC. And then that is then obviously fed out there. So just looking there just to see if I can understand it a bit more. That's the AF filter or something to do with that. AF scope, so again coming in there. Again another range switch here for AF scope and obviously bar chart probably. Gain circuit there. So yeah, I understand a little bit more about it now. So I think a couple of things. I think we need to look at the voltages first, start the basics, because if the voltages are not right then obviously the board's not going to work properly. So we'll need to check this regulator, because that supplies 9 volts directly to the FM discriminator, and we'll also need to check all these other voltages. So let's do that now. Right, so we've got the multimeter set up down here now, ready for connecting. I've got my earth probe on the chassis there, so just check some voltages. This is that little IC there that's generates the 9 volts, the LM317L. So we've got an input, output and adjust. So if we go on the input a second, just to see what we've got there, and we should be getting nearly 12 volts. We are 11.7, and then on the output, just being careful not to short it because it's on, we are actually getting 9 volts. So yeah, 8.873 volts, that's near enough. So that's producing that. These are supplies as well, so let's just have a look at these. Plus 5 volts, 4.944. That one in the middle is an earth, and then we've got this one. That's plus 5 volts. We have these supplies as well, and we are getting plus 12 volts, 11.7. This one plus 5 volts, minus 5 volts, and what's this, minus 12 volts. So all the supplies are okay, so I don't envisage that being an issue. So looks like the supplies are all okay. I can't see there being a problem there. Okay, so that rules supply issues out. So I think next test now, before we do any adjustments or alignment procedures on this AE7 DEMOD board, is we just need to make sure and check that the AF input socket on the front of the Marconi test set, the oscilloscope works okay for that, because obviously that, as we talked about with the A3 board, is a scope ranging functions, so that'll check that out. If that's off, then we've definitely got a problem, I think, on the scope board and not on the AE7, because obviously the ranging for the audio is via the scope board insofar as the front jack is concerned. So basically it will be this front AF jack. So if I just come back down here to the front and we look at this AF jack here, so if I go into what would be receiver test, and then we would probably need to connect in here. I've got my Rode and Schwartz set up to RX test at the moment. I just need to go to TX test so we can generate a mod tone, I think. Let's have a look. Just switch there, and I'll have to, yeah, TX test, and set up my Mod Gen 2, I think, on there. So I will look. See if I can remember how to do it. Mod Gen 2, 1 volt, and was it 1000 millivolts or something? Millivolts. There you are, 1 volt at 1.5. Need to set up the AF to 1 kilohertz. That's it. So that should be coming out now on the Mod Gen out. And so if I go to, we've got AF level there, and we'll plug that in this BNC socket now to the front AF port. So that's reading slightly high at 1.2 volts, but I think we can calibrate that. So 1.296 volts. Now there is RMS and peak options on this as well, but we'll just go to the audio analyzer a second, and go to the scope. So let's go to 1 volt per division, 2 volts per division, 5 volts per division. It looks off, but it's not. I mean, that's 1 volt per division there. Now what you've got to bear in mind with the oscilloscope on the AF measurement is that it's actually, if I remember rightly, it depends if it's set up to peak versus RMS, so I need to look into that as well. But the bar chart is reading relatively okay. Just above 1 volt, 2 volt, 3 there, so 1.2 volts. I'm only generating 1 volt, so it's sort of okay, is that. So it does look like as if potentially then the oscilloscope is off because of the sinusoidal waveform there. But I'll need to check into that to see how the scope reads and what the settings are in the setup, because I have come across this before on these, where in the settings you can have it to peak or RMS, and also into a different AF input load, be it 600 ohm or 8 ohm assumed load, which you'd have on the input externally. So I just need to work out, in reference to another test set I've got in here, that 2968 I've got sat behind. I just need to check its level there and just make sure that I'm not misreading it based on how the instrument's set up. But I should be able to go into the instrument setup and look at that a little bit more under user configuration, and in one of the settings you can change that. So I'll just have a look at that now. Okay, so just been reading the manual on it just to double check, and I've made a comparison check against my test set as well, but just for certainty. But basically, when reading audio signal with a bar chart, it's in the RMS range. Obviously, I'm generating from the Rode and Schwartz 2 volts RMS, reading 2 volts on the bar chart. But when we go to the oscilloscope, just put the expand on. We're obviously getting peak to peak, so we can measure that. Obviously, if we had to get peak 1.414 on top of the RMS, that'll give us the peak voltage, which is 2.828 volts. And if I move the markers, we can see there, just this little marker, if I move that down to the sort of minimum, we're getting near that there. Bear in mind, it is a little off anyway, because we're going to have to look at the cal signal that's used to cal the actual AF analyzer. But that's reading correctly. So peak to peak, it's around about 2 point, give or take, if I can just manipulate that a little bit further. Yeah, so let's just get that right into the dipper there. So you're looking at, yeah, near as damn it, 2.828 volts. So peak to peak, obviously that's reading correctly, whereas the bar charts read RMS. So that's what you've got to be aware of. I believe there is a setting somewhere deep in the setup menu where you can set that to peak, or you might not be able to. I couldn't find it in the manual, but I would imagine you can set that to peak or RMS, but I can't find out where you do that, but it'll be somewhere. So that gives the details on that. So the scope is working throughout the ranges, obviously. So it does point to me then, with the oscilloscope working and the bar charts working, it does point to me that there's possibly a fault then on the AE7 FM receiver board, or it could have been tweaked, obviously. So, you know, obviously we've got that issue, haven't we, where potentially we've got these potentiometers which may have been fiddled with, all these. So we're going to have to now look at the alignments menu and do some manual adjustments. I also am interested in looking at that cal signal that we saw as well in the manual, because I want to check the level of the cal signal for the scope. And if we just look at that a bit further again, and I believe the cal signal came in here, and I just need to see where that comes from, because I'd be very interested to find out where that's coming from. So it says there from, I think it's A2 with a look of it. If this manual's not very good, but I'm sure that says A2. So I need to look at what level that should be coming in and just double check that. Have a look how we calibrate the cal signal, and that'll set up the scope properly anyway. So I'll look at that. But yeah, so it does look more now as if it's something to do. We've obviously checked the voltage regulators and all these voltage lines, they're all working. So obviously everything's getting its supplies as it should be. Just zoom past that. The FM discriminator's getting its supply. I've not measured any voltages directly on the components yet, which I might do after I've done the alignment, but I think it could be now down to the alignment itself being off. These potentiometers might not be set up properly to give the right voltage, so we've got test points and procedures to go through as well. So we'll have a look at that next and see what that does with this adjustment as well, center channel offset and other things for the FM offset. These could all be out of calibration now if somebody's been faffing about with them. So I think that's where we'll look at. So the FM mod meter calibration is on page 3-24, and the AM FM absolute accuracy is 3.25. So just have a look at the alignment procedure now. We've verified the oscilloscope ranging is working fine. So that sort of rules out A3 board as being a potential problem. So we're back to AE7 now, the DEMOD board, and let's see where we get with that. Okay, so now we're setting a measurement up here as per the alignment instructions, which allows us now to perform FM deviation adjustments. So what that calls for is PLC, where this crocodile clip's connected to. That's the 10.7 MHz IF input, the pass-through from the spectrum analyzer board, which is this board. So that connects onto PLC there. What we've done, we've got the coaxial cable chassis braid connection, if you like, to the chassis, which is also connected to the neighbouring pin on that, because as we can see we've got the braid of the coaxial cable to the bottom there, so that would normally connect to the other pin, and then what happens is then we're feeding a signal in there on this coaxial cable. Now it says in the test you need to set the Marconi to TX test mode, frequency of 101 MHz. You select the RF in socket to be TNC, mod type is set to FM, and set the bandpass filter for the mod to be 0.3 to 3.4 kHz filters selected. Then we connect our signal generator, generating 10.7 MHz, which is this coaxial cable here, and this coaxial cable is connected to our Rode and Schwartz radio test set. We're generating 10.7 MHz at 0 dBm with no modulation to PLC, which is this socket here. Now we need to monitor, it says PLE, which is this socket here, where the FM mod would come out of, with a DVM, and we need to set it to measure DC volts and adjust R84, and R84 is this potentiometer here, to get a DC reading of 0 volts DC on PLE. So what I've done, I've just set up there the see if I can get that in the picture. We've got the DVM down there on DC volts, and I'm just going to go then to monitor PLE on. We've got the obviously here a chassis connection to the ground, and then we're going to go on to here, and we're going to measure the signal on PLE. We're currently getting 284 millivolts DC wise. So now we can adjust this potentiometer to get a minimum to 0 as we can. See, it's a bit sensitive. It's one of these things where you've only to breathe on it, and it's going the other way now, so we just a gnats off it. So let's just be careful here. I think that might be as close as we're going to get it there. Yeah, I'm happy at that. Okay. Now it says set the signal generator to provide 100 kHz deviation at 1 kHz frequency modulation rate. Set this up as accurately as possible by temporarily connecting a modulation meter such as an IFR 2305, accuracy of 0.5%. Reconnect the signal generator to PLC, set the DVM to monitor AC volts and adjust R90 for 2 volts RMS on PLE. So what we'll need to do now is we'll need to use a Roden-Schwarz test set, which can measure RMS volts rather than peak, and we'll monitor PLE. So we'll set that up now. Okay, so the next measurement is to set the signal generator to provide 100 kHz deviation at 1 kHz frequency, and then it says set the DVM to monitor AC volts and adjust R90 for 2 volts RMS on PLE. So where we were before, but we're just adjusting R90 now for 2 volts RMS. So what I've done, I've set up the Roden-Schwarz radio test set here, and we are measuring our voltage. We're obviously generating 10.7 megahertz at 1 kHz mod at 100 kHz deviation. We've got the weighting set to RMS. We're getting a voltage there currently of 1.5 volts, and so we now need to adjust R90. Now R90 is this potentiometer just here. That's R90, and that's labelled, I think, let's just have a look, as FM gain. That's what that's labelled as. So what we'll do, we'll just adjust. We've got the coax of truth connected directly to the PLE, which goes all the way back to the AF input on the Roden-Schwarz. So just going to see if I can zoom in on that a bit further and see whether we can see that signal better. So we've got 1.599 volts there. Just going to tune that pot then for 2 volts R90. So I'm just on it now with a trimming tool, just trying to get the thing turning. Right, tweak it for 2 volts. So we're getting there now, and we're nearly there at 2 volts. That's wonderful. Now obviously when there's no mod there, because it says as well, it says recheck R84 and optimize. So if I turn the mod off and then switch that to off, then put DC couple on, we shouldn't be getting any voltage. So I can adjust the other resistor now, the R84 to 0 volts. So I'm just going to turn that now to 0 volts, because obviously that was the R84, that was the adjustment we did the step before. So we've got to get that as close to 0 volts as we can, which is there. Then when I put AC coupling back on and the mod to on, we should still be getting 2 volts. So that's correct. So we recheck the R84 adjustment and optimise if required. Recheck R90 adjustment if R84 was readjusted, and obviously we're still getting 2 volts, which is okay. With the signal generator supplying 100 kHz deviation, pull the I2C connector off PLB. This will prevent the board circuits from being auto-ranged. Okay, so if we then look at the thing here, we've got PLB here. This is the control to the auto-ranging circuits on here, so we pull that off, okay, and then what we do, as it says here, we then with the signal generator supplying 100 kHz deviation, we pull the PLB off, which we've just done, set the signal generator modulation rate to 15 kHz, adjust R145 now for 2 volts RMS on PLE. So, where is R145, might I ask? Right, well, R145 is this potentiometer here, this one. That's R145. We'll just check that. Yeah, I'm sure it is, yeah. Yeah, R145. Yeah, so, back to the Roden Schwartz test set. And let's just zoom in there. Let's have a look if we can get a better picture. Okay, so 15 kilohertz, and now we need to adjust that R145. It's very low, is that? It's only 0.2 of a volt. So let's see whether we can get that adjustment back on R145. So it won't go any further that way, and we're not getting anything going the other way either. Now then, that's interesting. So we can't adjust it. So the circuit that's associated then with R145 isn't adjusting at all, no matter what. Now I'm turning it fully counterclockwise. Oh, it's about 20 turn pot. Right, I can hear the pot clicking now, so that's fully counterclockwise. It's not made any difference. We've got 0.299 of a volt. Now I'm turning it fully clockwise. I keep turning it until I hear the clicks again for when it reaches its absolute maximum, and still turning it and still turning it, and any moment now should be hearing some clicks. There we are, click. So minimum and maximum on R145 is making 0 adjustment at that 15 kilohertz. It says remove the signal generator, reconnect PLC and PLB. Yeah, so that's basically to put the I2C bus back on. So that adjustment then, R145, that one is not making any adjustment whatsoever, is that. So that's that step number 6. So step number 6 there, with the signal generator supply blah blah blah, pull the PLB for the I2C to put auto ranging, set the signal generator at 15 kHz, which we've done, adjust R145 for 2 volts RMS on PLE. So that step's not working. So we've obviously got a fault then with that part of the circuit. So the auto ranging would obviously switch on and off depending on the amount of deviation that's going in. So with auto ranging on, in essence, we're getting the right voltage as in the earlier steps, but with auto ranging off, by pulling that connector and 15 kHz mod supplied, we're not getting the 2 volts output. So that would explain why when we're at certain ranges in the scope that suddenly it kicks into life and we get the wrong mod level. Now that voltage was off, it wasn't nowhere near 2 volts, it was, you know, 1.1 volts or something, so we had to adjust that potentiometer R84 and R90 etc. to set that up, as you saw earlier. So we're sort of getting there now, so I just need to look at the circuit around R145 and see what that does, and then let's do some measurements around that with voltages and look at the diagram, see what's going off around that circuit. Okay, so where we're at now then, I've noticed something that's rather strange and unexplained, which I'm going to demonstrate. Having gone through all this, and obviously we got to the 15 kilohertz bit, we weren't able to achieve 2 volts RMS on PLE. At no point does it mention in this instruction to remove a plug from PLE, which goes off to AE3, which is a scope board. Now, what I find strange about it, which I'm going to demonstrate to you in a moment, it doesn't say anything in the first instructional part here about setting either the bar chart or the oscilloscope, nor does it talk about setting oscilloscope ranges. Now you'll see in a moment that has a massive effect on this measured signal, which, you know, I could have done with knowing in this instruction whether to monitor. It does say monitoring the audio at PLE, but it doesn't say remove a plug from PLE. Now it does go into great detail later on about saying remove the signal generator and reconnect PLC and PLB, so it does tell you when it wants plugs removing or leaving in situ, and it doesn't mention anything in this instructional diagram here about leaving PLE in place or removing it. So it just says monitor AC volts and adjust this particular potentiometer on PLE. So it's not saying remove PLE and then measure the socket without the scope board being loading it or anything like that. Now currently at the moment what we've got the Roden-Schwarz. This is just with, I've just put a 10 kilohertz tone on, but which I'm going to show you in a second, but with 15 kilohertz mod on, obviously we're not getting 2 volts, we're only getting 0.3 volts, just under, okay, 0.298 volts RMS, so we're not getting the signal that we need. And it says in the diagram, obviously, to adjust R145 to get 2 volts RMS on this socket here, PLE, and adjust R145 to achieve that. Now when we adjust R145, obviously nothing's happening, and that's R145 there. So R90 is working fine there. We can adjust that obviously for when we get 100 kilohertz deviation, and we can set the output voltage at PLE for 2 volts RMS, and obviously R84 works there when we're setting the DC offset when there's no mod present, so that all works, no problem. But we cannot get an adjustment on R145, so we'll have a look at that on the diagram. But there's this thing about auto ranging, and we'll see in a moment on the diagram. There's actually an attenuator circuit which switched by IC18, and IC18 does actually an IC1 drives it. IC1 is the I2C bus controller, so this switches low gain and high gain outputs off to an attenuator switch, which switches in the auto ranging circuits on this board. So we'll look at that on the diagram as well. But I think what I'm getting to on here is possibly replacing this board with a spare that I've got in my parts bin, and just trying that, because as you'll see in a moment what we're going to go through, it's a bit misleading. So when we first start the test set off from power up, which it doesn't describe this bit in the manual, it actually says nothing there about setting the oscilloscope or the bar charts. Now obviously if I go to TX test on there, if I select the scope, I've got different ranges I can select. So I can select 2, 4, 8 kilohertz, 20 kilohertz, 40, 100, 140, whatever, right up to 200 kilohertz. So at the moment, if I reduce that level down, we're obviously getting a sinusoidal waveform, and that's being captured there. Now the level is totally wrong obviously, but bear with me a second, because when we get to I think it's 20 kilohertz range, let's just see whether we can do that. So that's like 2 kilohertz, I think that's 4, 8, and then the next one 20 kilohertz. I'll just turn that volume down. It sort of overcompensates. It's as if it's auto ranging's not working, it's not attenuating. And we can keep going up, and obviously till we get to 200 kilohertz, and it says it's doing stupid deviation. And at the moment we're still getting the, if you like, the 2 volts or thereabouts. It's actually gone up now because of the oscilloscope. When I adjust the oscilloscope ranging back to what would be 4 or 8 kilohertz, it drops down obviously to 0.2 of a volt. Likewise, if I put that back to 100 kilohertz, where we're getting the 2 volts there, 1.99 volts, we can obviously see here on the oscilloscope a signal. And if I reduce the scope down to anything below sort of 20 kilohertz, the audio level on there remains the same. Now watch what happens when I adjust the oscilloscope now to 20 kilohertz plus or minus. Suddenly the voltage is shot up to just under 10 volts and we're getting a square wave. So that's obviously with the oscilloscope at plus minus 20 kilohertz. When I drop down the range to 8 kilohertz, obviously the deviation's still reading off, but now look at the voltage. We're now back to 2 volts with a nice sinusoidal waveform. So it's as if there's something wrong after the AE7 DEMOD board. To me, there's something weird. However, the test that we've got here does not say anything about setting the oscilloscope or the bar chart. So one must assume that when we first turn on the test set, it defaults to bar chart. Now bar charts are auto ranging, so right now it's auto ranging, so it's trying to set those attenuators I've talked about on the AE7 DEMOD board to find the best range, which is either ×1 or ×10 is the attenuator. And now look, when we look there, this is a default position that the test set would default to upon power on, is the bar chart. It doesn't default to the scope, and in that case it's now reading way off. And I've tried adjusting R90 to get the level down to 2 volts, and it doesn't adjust. It keeps that voltage. Now it's very strange, is that very strange. Now what I'm going to do while we're on camera still, we've verified there that by changing the oscilloscope ranges from 2, 4 to 8 kilohertz, the voltage coming out of PLE is 2 volts RMS, which it should be. When we then change the FM DEMOD from the deviation from the Sig Gen to AE7, from 100 kilohertz deviation to 15 kilohertz, we then still should get 2 volts output, and we're not. And it talks about here in this instructional of removing PLB which is the I2C bus control, which will auto range the attenuator circuits. And when we unplug that, whether it's plugged in or not, it makes no difference, but this is one of the things it says. This will prevent board circuits from being auto ranged. Okay, so that's fair enough. So basically, bar charts are default from power on, and it mentions nothing in the service manual about remaining in the bar chart mode or the oscilloscope mode. And once we return to the oscilloscope mode, everything's hunky-dory between 2 to 8 kilohertz. But the moment we press 20 kilohertz or above, then we get the distorted wave and the high voltage, which suggests to me something outside of this AE7 DEMOD board is causing an issue, possibly. Is it loading the output of PLE? It doesn't say in the manual to remove PLE, it just says monitor the voltage at PLE. So I'm going to do a measurement now with PLE removed to see whether it's some kind of feedback. Now it's worth mentioning at this stage, according to the service manual, on AE3 there is actually an FFT software adjustment and cal adjustment, which I've already done, and it passes the self-cal with no problems. But as we'll see when we look at the diagram, it'll explain it a little clearer. But there are attenuators and other software settable attenuators for FM DEMOD in the scope section, as well as the DEMOD bit we're currently looking at now. So there's two areas in the instrument where the FM DEMOD is sort of calibrated. So that's worth knowing as well. Anyway, I digress. So if we look at the manual again and we go to the discriminator section, I managed to find the section which looks at the attenuator, the ranging, if you like, and that's this IC18. Now what IC18 does is it gets an FM low gain signal, and essentially it's a solid state relay, but we were adjusting R90 here to get the 2 volts output at PLE RMS, which we could do. Now when we're injecting 1 kHz tone at 100 kHz deviation on 10.7 megahertz coming into this DEMOD circuit, essentially the 2 volts RMS that we're getting outputted here, I would have thought that it would default this switch so that the attenuator switched in all the time until it's auto, so it would always start off at maximum attenuation, I would have thought, so that moment it detects a signal which is lower in deviation, then it would then switch out this attenuator and pass a signal through. When the signal's obviously in excess of plus or minus 8 kHz deviation, then it will basically switch this attenuator through, and therefore any deviation higher than 8 Ks would then be going via this attenuator. So this attenuator obviously is an issue as part of the auto range. Now the FM low gain line is controlled from the I2C controller. If I can just find that again, which is up here, I think. Maybe next one. It might be the next one here, and it is here. There we are. This is it. So this has a, that's IC1, which is that chip I pointed out, and it has an FM low gain range there. So it talks in the service manual as part of that adjustment, before we drop the mod down to 15 kilohertz, it says remove PLB. So in other words, the serial clock and data line, serial data and serial clock, are not connected to the I2C bus. So in other words, it can't tell, the scope module can't tell AE7, the DEMOD board, to switch in or out that attenuator we were looking at. So obviously the attenuator itself wouldn't be activated in that mode, and I would then presume that the attenuator itself wouldn't be set, so that when we were injecting 15 kHz deviation, then essentially it would be passed straight through. So I think, in other words, with 100 kHz deviation, I think this attenuator switched in, so we get 2 volts RMS, and in essence when we then disconnect PLB to prevent the serial clock from adjusting that register, that shift register, from changing this FM low gain actuation, it prevents that from happening. So then when we drop down to 15 kHz deviation, then obviously the attenuator wouldn't be switched in, it would pass straight through, and we would then adjust R145 as it said, in order to set the 15 kHz deviation. Now if I can find R145 again, that's R84. R145 is frequency response on the discriminator, so R145 is here. So this R145, we need to set that to give 2 volts RMS output when the discriminator is detecting 15 kHz deviation. So I think, because the auto range doesn't seem to be working at all, I believe that the issue may be around this IC18, this sort of ranging switch, if you like. And this is what I'm sort of puzzled at, really. And I've just lost the diagram now. Let me try and get back to it. It's up here again. So I firmly believe that there's some issue around this attenuation here. It's not switching in and out. And I've plugged both connected and disconnected PLB from the shift register. When it's either running 100 kHz or 15 kHz, it's making no difference, and it should be, because it would auto range, and that's either in the bar chart mode or in the oscilloscope mode. Doesn't matter. So that's quite interesting, I find. Anyway, when we go to the oscilloscope board, which is here, PLE, the DEMOD FM, there's DEMOD AM and there's DEMOD FM. We know the AM's working fine, so I don't need to worry about that. But the DEMOD FM comes in through this 1 nanofarad cap into this op amp, and then is buffered. We have then another op amp here, and the audio circuits arrive at 2 junctions on this multiplexer. Now what the multiplexer does, it's got a cal signal coming in, it's got the FM signals coming in on both pin 15 and 9, and it's got the AM signal coming in on pin 2. So when you select the different mode configurations with its cal through the calibrate menu, and again we can see there the cal signal's also broken off to go into the external mod input to calibrate that, as well as other circuits as well. The cal signal comes in obviously up to that switch, so when we're in cal mode it'll cal everything after this, not before. So it's not calling the AE7 board at all, it's not calling that, and it's not calling the FM DEMOD side at all. It's looking for a particular AF level coming in order to reference that against a particular deviation, and that's referenced back when we look back at the diagram here, the explanation. The DEMOD is done on page 127, I think it is, which is right the way down here. 127, we'll just have a quick gander at that. So the FM channel, he talks about here, low gain controls provided by switch IC18, which also provides the means of connecting the squelch signal, which we could see the squelch signal there. that works, the squelch works, it mutes the audio, disconnects the audio through, that's no problem with that. However, it says that means if I connect the squelch signal to the A2 board, gain may be ×1 or ×10 as referred to in the section on AF, DEMOD and multimeter ranging. Now then, watch this. If I set my Roden Schwartz up now to do 10 kHz deviation, right, we've obviously got the 2 volts output coming out on PLE, which is what it should be according to the information in the manual. However, we don't get that obviously when I drop down the ranging to 8 kHz. 20 kHz and above, which we're at now, it's at 2 volts, which is wonderful. That's just wonderful. But anything lower than 20 kHz, like 8 kHz, it drops down to 0.2 of a volt. Now, obviously, if I was to increase that to 100 kHz, then it's correct. But as per the instructions in the manual, if that was set to say 15 kHz, that should be reading 2 volts, and it would only read 2 volts when we're at 20 kHz or above. It's actually reading a bit above there. So again, that's a misnomer. That's something I don't understand in the manual, how that's working. But anyway, I digress. So if I change that to 100 kHz, obviously at 8 kHz deviation selectable on the scope, we're getting 2 volts. However, if I select bar charts, now bar charts are auto ranging, we're getting 10 volts output at 100 kHz deviation on PLE, and at 15 kHz deviation we're obviously only getting, you know, we're getting a voltage there, it's 2.9, 2.8 volts. Now I can't adjust that. No matter what potentiometer I adjust in the alignments procedure, that will not adjust while ever the auto ranging is taking place. But what I would like to show you is this. If I set that to 10 kHz deviation, okay, and we then have a look at the front of the Marconi, you can see now that the actual deviation, FM deviation, if I just adjust the oscilloscope and we go down to there, so we can see it nicely, it's doing 1 kHz. So it's like got the ×10 divider in, attenuator. So obviously if I adjust the Roden Schwartz now to give us say 20 kHz deviation, 20 kHz deviation, and then I return back to the oscilloscope, you can see now that are reading 2 kHz. So the reference in the manual there, the gain, which it talks about, which is this bit here, the ×1 ×10, is actually controlled by that attenuator switch, which is this. So there's something strange going on around here, and the auto ranging doesn't seem to work until we get to about 20 kHz. And once I select 20 kHz on here, so the sinusoidal waveform remains the same on 2, 4 and 8, and the moment I hit 20 kHz, now it's jumped up to 3.9 volts. And obviously if I keep going, it's still 3.9 volts on the oscilloscope mode on there. So I don't understand that. The manual does not tell you about whether you should select scope or bar chart, but all I can tell you is bar chart is actually selected when the instrument powers on from fresh, not the scope. It defaults to that. and as we can see, we're getting a rather silly FM deviation there. So I've no idea whether I'm doing it wrong or whether the service manual's got an error in it. Normally Marconi are pretty good with their service manuals. It mentions nothing in the alignment procedure about selecting oscilloscope ranges or bar charts. It doesn't tell you anything about that. And what I've done off camera as well, I measured PLE. You know when we're getting that 9 volts? Well, that's not present when PLE is unplugged. When you take the plug off that socket and you measure on those pins directly with the oscilloscope on the Roden Swartz, it's not reading 9 volts. So it's as if that voltage is coming back to the AE7 board from the scope board A3. So I am at a total loss now as to what the hell I should do. I've no idea whether the measurements I'm making are correct. The manual doesn't tell you about disconnecting PLE or plugging it in. It doesn't tell you about whether it should be auto ranging with the bar charts or with the oscilloscope or anything like that. And if you do follow the alignment procedure just with the bar chart on there, and you follow that alignment procedure on PLE on the underside board, it doesn't make the voltage change anyway. As a matter of fact, when it's giving 9 volts output on that deviation at 100 kilohertz, when you try adjusting R90 or R145, it doesn't adjust at all. You cannot adjust it beyond or any lower than 9.5 volts, and that square wave's horribly distorted, obviously, as you can see when we were looking at it earlier. So there's something strange about that. So, you know, obviously there's a real problem there. So I think what I'm going to do, because I can't keep going round in circle after circle after circle with this damn thing, I'm just going to get another board out my spares bin and I'm just going to plug it in, and I'm just going to see whether the problem is actually on this DEMOD board or whether it's on the A3 board, because I haven't a bloody clue what's causing this problem. Before I start hacking ICs off and measuring logic lines coming out of the multiplexer for the I2C serial bus, I'm not even going to go down there until I've verified whether the problem's on this board or not. But yeah, the manual's not very good when it explains how to do that measurement. Now, it could be I'm over analysing it, you know, that's highly possible. We've obviously got the discriminator as well, which I've measured voltages on off camera. We've got the discriminator here, runs off a 9 volt rail, it's getting that. I've verified that voltage. These two Zener diodes here as well, which are 6.2 Zeners, they're often common failures on many things. They're giving 6.2 volts out. We've got obviously that R145 there. That does not adjust at all in the measurement which is described in the manual. I am getting audio. This is a filter that filters off the 700 kilohertz IF signal and the first harmonic 1.4 megahertz. That filters that out, so you just get the audio coming out here, and then obviously that goes off then down to the next part of the circuit. That's that DC adjust offset thing, which we're working fine. And then the FM mod comes in. We do have that R84, which adjusts to the DC offset, which comes out then on PLE. That all worked fine. So the FM mod from the circuit we're just looking at a moment ago, that 700 kilohertz filter, comes in there, and that's the R90, which does adjust when there's 100 kilohertz coming through, but there's no adjustment on it when there's only 15 kilohertz deviation coming through. And this doesn't seem to me to be switching. I mean, it could be, I don't know, I haven't measured it yet to see whether it is switching on and off, but it doesn't look to be. You know, if the auto ranging was working, this will be switched in the maximum attenuation all the time, and then when you drop the attenuation down, drop the deviation down in level from 100 kilohertz down to something like 10 or 20 kilohertz, this will then switch out the attenuator and allow the signal to pass through. Doesn't seem to be doing that. So whether it's a fault here or whether it's a fault in the I2C controller, which is up here, I believe, it could well be. Here we are, this is it. Whether it's a fault in this IC or what, I don't know. It may be there's a communication problem with this IC. It's not getting any serial clock or serial data. Bearing in mind, of course, somebody else has been in this test set. Perhaps this connector, wherever that goes off to, has got a broken connection, and maybe it's not getting any data to control the ranging. So I need to consider that as well, because somebody else has been messing about this test set. So there's a few things there, but I do believe that to be working, because when I adjust the squelch signal, the squelch control on the front of the test set, the squelch line does actually work. So, and obviously the squelch line is controlled by that AGC fast. So that looks to me like as if it is okay, that IC. I could be wrong, you know, I might be barking up the wrong tree totally. I think the easiest thing before I start hacking this board to bits and doing more in-depth checks and tests and leading myself down various garden paths, as I say, I'll just swap the board with one out of a mid parts bin that I know to be working, and then do that. I think that'd be the easiest thing to do, because everything else seems to be there. I'm just going back down here just to check where that squelch circuit is. Set squelch. There we are. So yeah, that set squelch does not appear to be coming from that IC that I've just been looking at. I thought it did. PLM pins, it comes from a different socket. So yeah, it could be then that the that controller is faulty, or it's not getting comms, you know what I mean? So that's a potential issue. So if we just nip back there a second, just have a look, because I'm confused as to what the hell's going on. And that's why it purposefully says in the alignment menu, remove PLB before you inject your 15 kHz signal, so it doesn't auto range. But that also, that instruction is reverse logic to what I thought, because I would have thought with 100 kHz deviation coming in, the output of this would be switching that attenuator on. So we're getting maximum attenuation, you see, through that attenuator switch, this. So I would have thought with 100 kHz deviation coming in, this will be switches through this attenuator out, and then what you would do then, you would inject 15 kHz, and then this switch would close, so therefore there's no attenuation, and then you would obviously adjust the other potentiometer R145 to give 2 volts output. But what it seems to be suggesting in the manual is you start with 100 kHz deviation. It seems to imply that this wouldn't have any attenuation at all, and then when you adjust, you unplug PLB to prevent this from actuating, inject 15 kHz deviation, which is a lesser voltage that will be present on here anyway. Obviously the higher the deviation, the more voltage we're going to get on this line. The lower the deviation, the less voltage we'll get. So for me, it seems reverse logic that you should unplug PLB for the IC squared controller when you're injecting 15 kHz. If anything, I would have thought it'd be the other way around. So you're getting the maximum attenuation when you're reading 100 kHz deviation, and minimum attenuation when you're dealing with 15 kHz. But when you read the manual, it seems to imply the complete opposite. So I have no idea how the hell that works. Whether there's another, as I've already explained earlier on the oscilloscope, there's other ranging that's taking place after this bit, I don't know, but it just seems a bit strange to me, does this. I can't work it out. It's got me as this, I must admit. It's got me, because it comes into there, and then where is it now? Is it that one? Yeah, that's it. Comes into this, and then basically it's then going out through this op amp. So this is the oscilloscope board, and then it's obviously called DEMOD filter in to sheet 4. So after it's gone through all the selection, whether you're going to obviously select AM, FM and all that, these are the control pins, it then gets routed then to that. So I don't know. That seems to be the DEMOD anyway. And I sort of have to try and find where the DEMOD comes in and what have you, but even before I started down that route, again, I'll be barking up the wrong tree until I know that board. Again, AF programmable gain, there are different attenuations that are switched in. So it's a two-part attenuators, one on the AE7 board that's arranging, and then there's another one which is on the oscilloscope board as well. And that 9.5 volts isn't coming from the AE7 board at all, because I've unplugged PLE. This connector here that's on this board, I've actually disconnected that PLE and measured the signal after we've received 9.5 volts where it's connected now. I've unplugged that and then looked at it on the scope, and it's 0.2 of a volt again. So that 9.5 volts ain't coming from this board PLE, it's coming from AE7's PLE, it's coming from the A3 scope board. There's something being fed back from the oscilloscope board, because if it was loading it, that measurement would still be 9.5 volts when the PLE is unplugged, and it isn't. There's something very strange going on here. Right, back some, and I put another board in. Okay, so we've fitted new boards now in this, which are known workers. These are the boards that I've taken out the instrument, which I've labelled as F440, including AE8. I've changed them as a pair. So we've got a known working good board in there now, and everything's connected up as it should. Now, what I've noticed is a problem still persists. Now, I've set up a test on the test set where we're linking the RF in and out by this configuration switch. We're generating a signal out there at high level into the TX monitor input on the N, which we've configured it for. When our RF in out test, or you can do it duplex mode, either way. But as you can see there, I've set up the RF Sig Gen 150 MHz at plus 10 dBm. We've got the Mod Gen frequency at 1 kHz with a deviation of 30 kHz deviation. Now the TX monitor side, this bit, is now reading what it's receiving, and the FM deviation is at 3 kHz. So it looks like as if that times 10 times 1 auto ranging isn't working. Likewise, if I reduce the Mod Gen level of the RF signal generator to 10 kHz, then we're only getting, when I adjust the scope, so it reads within its range, 1 kHz there. And so that's looking like as if that times 10 switched in permanently, the attenuator, and it shouldn't be. So that's interesting. However, when I go to bar charts, now the bar charts is reading 1 kHz as it should be. So that's interesting. It's not reading silly modulation or deviation like it was before. So there's a little change there, a little subtle difference. So it could still be an issue on AE7 depending on how we go through the cal routine, which I'm going to take you through in a moment. But anyway, 10k is in with 1k out. Obviously if I put in 50 kHz output, then this will jump to 5 kHz. So it's as if that attenuation is not reading, not switching correctly. And obviously everything works, and when we get to 20 kHz deviation, then it goes silly, you know, up to 200k is there. So it's as if, yeah, it's not attenuating the signal. It's doing some weird stuff, is this, I must admit. So it could be and it's something quite easy to check, I suppose, now, because obviously whatever problem there is going to be external to this board. But this PLB, the serial data and serial clock lines there, I should be able to go onto those serial data, serial clock, to see data strobing on them, because it could be that with other people being in this faffing about before me, it could be these data lines going back to the I2C bus are broken. There's a plug damaged or somewhere else in the test set I haven't got to yet. So I need to check these two for data, and I might be able to monitor pin 10 there or whatever to see whether the FM low gain's working. So it does seem a bit strange to me. It may be that the I2C bus isn't working here, so that could be a potential issue. So there's a few things there really. I can't see where else there'd be an issue. Obviously the auto ranging is working better at the moment in this particular config, but there again I am actually setting up a test here where it's testing itself and everything's connected as it should be, whereas the measurement we're doing before, we had things unplugged and we were injecting signals directly on the board. So it might be the test set performs differently because some of the connections that it relies on to sample mod in different ways is being disconnected. So but yeah, the bar charts bit there at least is more stable than it was before, because it was just maximum all the time on the bar charts previously with the other board fitted, and it just read maximum mod all the time on auto ranging. So something has possibly improved here. The only way I'd know for that is if I put the original boards back in and set this test up as we've done now, using the RF in out connection there to verify if that's the same. So I think what I'm going to do now, while we've got this new board in, the known working board, I think what I'm going to do is I'm going to go into the Marconi service menu. I'm then going to go into cal values, and I think I'm going to go and run these audio and DEMOD cal sequences, and I'm going to run all these filters and mod setup and things, and obviously I think I'll do the scope and FFT as well, and we'll do those cals too, recal it, because when we looked at the there is a parameter where you can do the oscilloscope cal as well. So the calibration for the oscilloscope, this cal signal that comes in here on that line, you can actually calibrate that value, and there is somewhere in the service manual that tells you how to do that. So it talks about adjusting the oscilloscope, because this test that we're doing now is final adjustments on AE7, and this is where, after you've done the measurements that we've just made, you would do this test I'm doing now, which is you go into RF test, in out, toggle RF select, 2-port mode, you set up your Sig Gen, and you set up 150 megahertz, and you do a very low frequency tone of 100 hertz, 90 kilohertz, 100 hertz frequency, 90 kilohertz deviation at 100 hertz frequency, and then you're looking basically for that particular measurement to be in place. So basically that would be this. So we go return back to that TX mod thing there, and we will go set mod gen level 90 kilohertz deviation at a frequency of 100 hertz, and we would set then the bandpass filter to 300 hertz low pass, and we should be getting 90 kilohertz, and as you can see we're getting 9. So that again is a times 10 function not working with regard to the attenuator, so that again proves that. But at least we're getting closer now to what potentially could be the cause. It could also be that if AE7 board that we've just replaced has got a fault on it, because obviously the auto ranging wasn't working, We were calibrating it earlier before we started this section of the video against what would be a faulty board in the FFT corrections. So obviously when we rerun the scope FFT calibration, it would calibrate it against a known good reference. So there is that. So we might just run that cal sequence again now with this board in it, but there is there is a calibration sequence here. I think it's DEMOD 100 kilohertz. Let's have a look. Self-calibration information, peak detectors, DEMOD, FM, drive sensitivity, FFT, calibrations, 4.54. So 4.54 roughly. Here we are, look. So this is what it does when it sets up that procedure. Calibration procedure, initiation, this is the auto, set frequency to 5 kHz at 1 kHz division, vertical scale, it's a ground path for that, remove cal ground signal to A3 AF path input, start measuring points, goes through all this. So the cal signal is available, gain offsets, and again there's different gains depending on what it's doing here. 1 kHz division, 10 dBs. Because I said there's some more attenuators in this as well, in the calibration bit. And there is a calibration procedure, broadband power meter. Oh, that's different. Calibration procedure performed each step. Right, so I believe there is an oscilloscope, horizontal deflection circuits. I'll find it. Control circuits. Just trying to find the oscilloscope. I did see it earlier. You see things when you're flying through manuals and you think, oh yeah, I remember that, and then when you need to refer to it, it's because it's A3, so that's AB4. It'll probably be right down here somewhere. Let's have a look. Must admit I'm messing about here a bit, but A4, so it must be before this. AF filter, that's it. Yeah, this is it. Technical description. I2C controller, A3, demodulation filters, and AF filters, external modulation input gain, DEMOD select. Here we are, look. The DEMOD AM and FM input signals from AE7 board. FM signal is buffered by the unit's gain amplifier C14 and splits to provide FM pulse modulation, phase mod, sorry, and AM and as well. I think there's a typo there. It will be AM and PM. Integrated circuit so and so. Under software control switch, so selects either AM, FM, PM or CAL. The unit gain amplifier buffers the signal to provide the DM filter in signal to modulation, programmable gain and filter circuit. So this programmable gain bit is what gets called when you're doing your calibration routine, and it does, there is in the FFT calibration, it does talk about in the FFT calibration about how you set up the calibration. So that must be further down. This must be in the cal sequence for the FFT, which will be down here somewhere when I find it. That's it. I think it's further up here. Right, so I think we're near it. Right, so hardware, list of figures, IFR. Right, I'll just see if I can find that. Okay, so we've got a bit of the alignments bits brought down to hardware alignments versus software. So this is the FM DEMOD FFT gain offsets calibration. So we basically would cal values in their scope FFT, cal config, DM FFT offset. Calibration was used to calibrate the gain offsets of the FM DEMOD FFT. The calibration works by relying on the accuracy of the 1-bit ADC low frequency FF generation in the signal generator for various DEMOD FFT reference levels as shown in the table below, and talks about that. Calibration sequence, obviously when it runs the cal, and I think that's about it really on that. Calibration procedure, FFT gain, I'm not sure whether DC marker obviously, and there's even more up here somewhere. External AM gain, and keep going. External modulation FM gain, calibration, mod input signal for FM. The calibration of the DC FM capability is a fractional end chip AE1 after performing FM nulling. DC blah blah AE1 drive coupled FM selected. That's for external modulation though, that. External modulation calibrations, crystal filter gain, so that's mainly for the spectrum analyzer. I did see somewhere, and I'm struggling to find it, there was a calibration for the cal signal for the DEMOD in the scope FFT, and it talked about going into a particular menu and then adjusting the DAC so that it would then give a proper reference for the cal. So you essentially would monitor the cal signal at a particular location, and then you would then adjust using the software DAC in the Marconi menu, calibrations menu, to adjust the signal level to the right level so that the gain is set correctly for the cal signal. And it talks about the RF calibrator, that's something different. Audio generator calibrations, self-calibration information there, select to deselect path, phase modulation. Anyway, it must be in there somewhere, but I think what I'll do is I will just run this cal sequence, which takes about 40 minutes, and we'll just let that perform its cal and let's see what happens. And in the meantime, while it's doing that, I'll see if I can find some more info. Okay, so where we're at now is I've just off camera, I've just gone on to IC10, which is here, and I've measured on pin number 10, sorry, IC1 pin number 10, I correct myself, and the pin number 10 is this island here, and I've gone on to that, and that's the times 1 times 10 attenuator switch, which controls the ranging on this AE7 board. Now then, what I've done off camera is, because we're at the same stupidity that we were before, I've measured on that island, and I can see when I flick the ranges on the oscilloscope, we get some burst of audio as it over deviates the oscilloscope. Suddenly this logic level on this line switches to an active low, and when the oscilloscope's adjusted to a lesser range on the ranging, this then flicks to the opposite logic state. So this is working, and there's no reason to doubt that now. So it looks like as if the other issue then might be, as per the technical description, on the A3 board, which is the audio processor board. And I wanted to now leave that as it was and then move on to the next board that this feeds, which is A3. And A3-1 is the board that does all the audio processing before it's passed to other boards for dealing with. And A3 also has programmable attenuators and offset attenuators with DAT values that are programmed as part of the calibration routine on the software cal on here, as well as the hardware cals that we can do. And there's all sorts of FFT ranging and various other things. Well, A3 is on the opposite side. So this is A3. And we'll just get the test set turned round so we can see it. Now, I haven't taken these boards off until now, but I wanted to remove A3, which is this board on the top. And obviously I've been in the process of removing that in order to swap it with a known good one from my other parts bin. Now, in doing so, I've noticed something. Obviously, I've not checked throughout the test set deeper in this sort of side, the top bit, deep down, to see whether all the boards have been connected in properly. But anyway, what I've done, I've just had a quick look here, and I think I might be able to get some more lighting and show you this better. But, if I open this board up, that's obviously, you know, A3 per se, which we've got there. That's the underside of A3. And then this board here has got something interesting on it. And let's see whether you can tell me by looking at that what is interesting about that. Now then. Now, if we look at the connectors, for example, on the lower side of the board, we've also got a label here. So again, somebody's been in even to this level. But looking at these connectors here, particularly this one and some of the others down here, they're not even touching, they're not even connected. The pins are just massively pulled out, as if there's been some excessive strain put on them. And you can see there, so there's no way that's connecting. These end pins can't possibly connect into that. You might be able to get away with it down there with that one, but again, even this one is really off. The other ones are also skewed. That one is, but it straightens up without a problem, pushes on. That one's okay. So those three are sort of okay. But there's no way that's going to connect. And it just seems so peculiar. Let's just see whether we can have a look at some of the others as well. And I'm like, why is that? I mean, what the hell's going on? It's like as if this entire wiring loom has been yanked to something. So I don't think they would connect. Certainly not that one. So we're not getting connections going off, you know, to important parts of the circuit board and other systems. Whether that's like it as well on the other boards, which lay underneath, remains to be seen. But if I just zoom out a bit, it's a bit dusty as this one. But I can certainly remove that and check that as well. But it looks okay, that one. It's just this one. Again with these connectors that are totally off. So a couple of them, these two in particular. So I don't know what's gone on there. It's some kind of torsion, and it's yanked against them. So I'm gonna have to look at that, obviously, and those two, and free them up somehow. I don't know what's gone on there. I think it's just one of these things where, you know, we've got a situation where some strain's being put on. I'm just gonna remove this board now and unhinge that to see whether that also has a problem underneath. But it would certainly explain a lot with this audio ranging issue. Now, A2 board is an audio processor board, but it's not fitted on all models apart from the 2965 and the 2967 or 66, which this is, 66A, has an A2-1 board, I think it is, or something like that anyway. So let me just see if I can slacken that off a little bit there, just move that round so it doesn't hit. So let's just have a look in there. So we've got a connector there which we will need to remove in order to see that, but that all looks okay. That's all pushed on all right. All these, certainly something that I need to just check into with all these boards, including what might be sandwiched down here, because this is a processor board at the bottom. So there's definitely something been going on there. But I can't understand how it's passed its audio cal and everything if those plugs are off. They may be causing all kinds of untold issues. It could be that the calibration signal enters, because I think it's the A2 board where the cal signal is generated, and that's then injected into these into the A3 boards. The A3 board itself, which is on the top here, this is the A3, and it's connected into here, the cal signal, for the input switch to get its calibration. So for all I know, it could be calibrating against nothing. I don't know, but that's certainly not good, is that? Where these connectors have gone totally skewed, and there's something not right there. I can put a multimeter into the sort of gold contact, you know, just to prove a point on that little spigot there, and then onto there to see whether there's any anything, you know, because there is a I'll just have a look there on my little zoom. That end pin there is, it's not like it's a ground or anything, it is actually a coaxial cable entering there, as you can see on the end, so that's carrying a signal, and there's no way that's going to be connected in a month of Sundays. Likewise with this one. So, and obviously somebody's been into this level, because there's an A sticker written on there for PLA, and that's not what Marconi would do. So this is the audio processor board, is this one. And obviously if it's not getting an audio signal fed in there, probably it's not going to do the auto ranging properly. And yeah, so that's very strange, is that? Obviously, yeah. So before I replace that A3 board, I'm going to try my luck, and I'm going to see whether I can free up that cable down here. It's these cables, you see, these coaxial cables, as they're entering in, they seem to be getting strained somehow, so I might have to cut all these cable ties down there, because something's yanking it, you know, and it's obviously hinged back in the test set where it should be. There's some strain being put on it somehow. I'm going to have to somehow unclip these and sort them out. So whether somebody's added these cable ties, they look original to me, but who knows. But there's definitely some strain being put on that board. Right, back soon when I've sorted that. Right, well, we've straightened those connectors up and pushed them back on, but I don't think I'm going to be as lucky with that, because I did put my multimeter on between the pins and the socket contacts, and they were connecting even though they were way off, you know, sort of out of alignment. They were still touching, unfortunately. I think the test set's sort of saying, so long sucker, if you think you're going to repair me, think again. But yeah, so let's just check it anyway. So I'm just going to go on to TX test and then select the thing. Let's see what mod we've got. Yeah, it's gone to 121 kilohertz. I'm injecting 100 kilohertz deviation at the moment. So yeah, but I'll show you anyway what I did with the IC1, which is this will prove, you see, that the I2C bus is controlling the AE7 board. So I'm just going to see if I can get that voltmeter. Now if I go on to pin number 10 on there, pin number 10, which is obviously, I get my little magnifier so I can see myself. That's pin number 10 there, and we then put our earth probe on, obviously, our little crocodile clip onto the chassis, which we got there. Right, so if I adjust the scope ranging now, you might see in a moment, I just go over to there, I'll just adjust the scope ranging. Go to oscilloscope first, it would help, wouldn't it? There we are. So with the oscilloscope on one range, it's increased the logic level to 5 volts, and then as we can hear the tone there, and once I adjust it to the next range, I'll just turn the volume down, it drops to logic 0 obviously, and then when we up the scale again for auto ranging, it goes up to 4.9 volts. So what that proves is that as we adjust the oscilloscope ranges for the deviation, we're actually, just demonstrate this a bit better, let's just alter the scope position. There we go. Right. So when we get to that position there, which is the 20 kilohertz, that's when it alters its logic state. And when we get to the 8 kilohertz or lower, the logic state switches again. So that's switching that times 1 times 10 switching on AE7. So obviously that proves that it works the I2C bus to PLB on AE7. Which was obviously the data bus connection, because I was considering, I did measure as well on the oscilloscope, but it was quite hard to see it because its data burst is quite quick. On PLB, this connector here, there's a serial clock and serial data line and 2 grounds, and that obviously is the data bus. So without trying to look at the data words that are conveyed on that, I just wanted to prove that must be functioning, because when we go on to pin 10 we are getting a switch. If you unplug PLB and then do the same checks again on the oscilloscope, you find that the level doesn't change onto IC1 pin 10. So it proves that the data bus is working, and there's no reason to doubt that, obviously, because the board that we've got in the test set is a known worker from my spares bin. So now that we've established as well the boards that are in the lower down, the A2 board, the A2 and the A3, which is this one on top, the connections are all okay now, and it's still not working. I'm going to now change the top board, A3. We've got a lot of tantalums on here as well, so yeah, that's also a cause of faults. But I just want to do some board swaps now until we get the thing working, and then we can pinpoint then further once we know which board the fault's on. Back soon. Right, so we've replaced the A3 PCB at the top here, and then the one that's underneath, which is A2 from our known good working spare. And the scope's still reading off, I'm afraid. It's exactly the same fault as before, and this is even after we've done the recalibrations of the audio and FFT. We have gone into the Marconi service menu and cal values, and we've done audio and DEMOD cals and scope and FFT cals. They all passed okay, and then what we did then after that, we did a reset and reset the instrument. Now we then connected a signal up following the cals of A3 A2 board, and as you'll see in a moment, it's made no difference whatsoever. So if I just select TX test and then select the signal input, all we're getting is 1 kilohertz deviation on the bar chart, and again we're getting this similar thing there where with the scope on, the ranges are all out, you know, obviously 4, 8, then we're getting that over mod again at 20 kilohertz and above, but we're obviously injecting 10 kilohertz deviation in and only getting 1 kilohertz out. So again, it's that times 10 thing, and the auto ranging doesn't seem to be working, you know, so that's a major issue here. So it's still off, I'm afraid. So we've got in the test set now a complete working AE7 board, which is the FM, AM and phase modulation SSB DEMOD boards, and AE8. We've got A3 board, which is the audio processor, if you like, and the A2 board. Still the same, the scope and the audio processor cards are being replaced. The only card left now, I think, is the A1 board, which is the DSP digital signal processor board, and then after then it'll be that card that had the defective socket on it, which does some of the audio switching, but I doubt it will be that, which is it's got the calibration features on it and things like that. So but basically we are really struggling now, really struggling. So obviously I'm going to be in a bit of a pickle soon. So the only boards we haven't replaced is this board, which goes to the front socket, and also the A1 board, which is this, and then that would essentially be all of them then. So I'll whip out the A1 board on our test unit, and then what I'm going to do then, we'll have a set of all 3 boards then within this from a working good radio test set, and then after that, if that doesn't work, it's obviously this board here then that we'll need to swap, which is the audio board. Now if that fails after then I think we are stuffed. There's nothing more we can do, because it must be either a firmware or a software issue, perhaps a corruption. It could also be the microprocessor board, there's some issue there, some loss of data somewhere, or some corruption, or something far more serious wrong with it. So, you know, I'm going to be limited then as to what I could do. So right, let's swap some more boards then and see what happens. Right, so we've put in the replacement working board. The original one that came out is quite dusty, but it's still got the same issue software on it than the board that's gone in. So obviously there's no incompatibilities then between the different firmware versions and things on the board. So yeah, we've replaced that now. That's a known worker. That's a known worker, which is A2 board, and then A3 is a known worker. So all three boards have been replaced to do with the audio. So I think what we'll do, we'll rerun the cal sequences again for the scope, FFT and the DEMOD. We'll do those recals, then we'll measure again. If it's still faulty, we'll change this board, which this board is a card reader, and also this bit here does AF ranging and the cal standard for the audio as well as the RF side of things. It controls all that, the calibration. So you never know. I just want to rule that out, and it's quite easy board to replace, so we can do that. The only other board that's underneath here then is the processor board. Now, in any case, each one of these boards costs several £100 to replace. So even if we do find one of these boards to be wholly defective, the chances of a customer wanting to pay several £100 for the board plus the labour, you might be looking at upwards of, you know, £1,000 repair cost now, if we do find the faulty board. But there's a couple more boards here on the bottom. That's the microprocessor board and part of a spectrum analyzer, and again that's the processor and memory, etc. as well on that. So there's a couple more boards there, but beyond this level it will be a write-off, I'm afraid. It's just not possible with the amount of time that's currently being spent on it to fault find to that sort of level. There's already been several hours of labour time spent on it already, and we're getting to the realms now where I don't think the customer's going to want to pay, you know, for the labour and parts. So we're really clutching at the straws. So let's give it a power up now. We've replaced these three boards that are just solely to do with the audio and DEMOD side, and if it doesn't work, then it's obviously a far more serious problem with the processor control functions or something like that that's going wrong. Maybe a software level fault or something with the processor cards, I don't know. But either way, several hours into it now, and it doesn't look likely that the repair costs are going to be cheap if we were to continue beyond this point. So let's see whether this works. If it does, then we're on a winner. At least then we can start component level fault finding on the this board here, the A1 board. Obviously A2 and A3 are working, so take it from there. Back soon. Right, so where we're at now is we've run all the cals again following the last step. We've then reset the instrument, and then I went into the user cals, which are these user calibrations, and I reran all them, and then I reset the instrument, measured again. It was still the same, reading 1 kHz with 10Ks coming in. So I think what I'm going to do, I'm going to place all the boards back in that we took out, and put it back to its original state where it was at, because I'm now convinced that with all the boards that we have currently replaced, which is obviously A1, that's digital signal processor board, then we have A2, again the scope board if you like, and then A3, which is also part of the scope, audio gen, and everything's on there as well as on this board. And then obviously we had AE8 and AE7, which is that board, and this board here. They've all been replaced and the measurements are the same. So I'm sort of convinced now that this has got to be a software issue of some degree. So what I'm going to do now as a last resort, before we read this test set its last rights, is I'm going to we're going to, I think it's there's production values, production setups and production values, but there is also under clear mem factory default, cals and reset. And we've got all these different resets, you see, including recall the factory preset default values and all that. So I think I might do the top one, factory reset, after we've done the done that, and then go through all the cals, run all the cals then for all the systems, and then have another go, because it could be just software corruption after all said and done. It could be so many things, but we've replaced most of the hardware that's in the instrument, all the boards, and it's not made a difference. So it's got to be software, I think, but who knows? So just have to see as a last resort. Never know, might drop unlucky. There again, we probably won't. Okay, so we're all back together. I've got the original boards back in now that we didn't have before, and we can now go to the reset function, Marconi service menu, and then I think if I just do that light a second, it was clear mem, factory default and reset, so total default, factory default reset, NB, NovRAM, E square prom, cal data all reset, E square calibration data reset to default, instrument will require recalibration. So cal data as well, yeah, that's it. So factory default, are you sure? Press key to commit. Yeah, there we go. Right, so we'll start again then. We'll do all the cals right the way through, and we'll see what if anything that does. Could be a software corruption, and by doing this reset and reinitialization, it may actually resolve the issue. So now we can go into help setup menu. The user calibrations at this stage are immaterial, because we need to do the factory level calibrations, but I'll just enter the code in for that. And then that's given us the extra menu now to get into the Marconi service thing, and then we'll go down to cal values, and what we'll do, we will do all of them, I think. Signal generator, audio generator, so just have a look there. So we'll do each one in turn, and all the way down the other side till we've done the whole lot, and then I will come back to you and see whether we've got it fixed. Okay, so we've run through all the calibration sequences. We've done a full, obviously, reset, run recals, after then stored data, reset the instrument, gone then to do a measurement like we're doing now, where we're generating a frequency, a level, and also a mod frequency and a level at 2.5 kilohertz deviation. But as you can see, still not reading correct, on FM. So we're going to have a look at what options there are now around one of the other boards, perhaps replacing that and seeing whether that resolves the issue. But yes, it looks like as if unless, you know, we strike lucky with another board that we've not yet replaced. Upon replacing that, it suddenly works. It looks to me like as if we're going to have to let this one go back to the customer unrepaired, beyond economical repair, because it's just not going to be possible spend any more time and effort on it. So let's see where we get to next. Well, at last, a bit of good news. We seem to have got the mod back working now, after we've done a board swap, which I'm going to go into. So we're generating on the HP Agilent behind here 100 MHz signal with a 3 kHz FM deviation, and we're getting that signal here, 3 kHz. The mod's back as it should be. Obviously, if I increase the range to 8 kHz, it gets lower, and we've got 3 kHz there. 20 kHz at that point with the other board in, it would have just, over deviated, and also 40 kHz over deviated. So the ranging's working. Obviously, if I change it from the 4 kHz in the dotted lines down to 2 kHz, it's over modding. The bar chart auto ranges as it should do. We're getting the 3 kHz deviation there observed. So the auto ranging's working. If I disconnect the RF signal completely, from the test set, and then reconnect it, then the auto ranging should work back again. So that's good news, and that's of course even without doing the software calibration in the Marconi for the scope FFT, which is what the fast Fourier transfer measurements are for the deviation and demod. There's also an audio and demod, which sets up all the filtering, etc., for the different filter parameters as well. But anyway, the long story has been cut shorter now, because obviously we've managed to get the deviation back, and the cause of the problem appears to be the microprocessor board. And I did read in the technical description, so this is the microprocessor board that originally came from this test set, and I put my spare in at the moment, which has got it working. So according to the technical description, as we've seen earlier, and we were following it through in the video, A3 board, which sits at the very top of the test instrument in the flip back cage, which is this bit here, this cartridge. The A3 board on the top here is the audio processor board, and that's where AE7's transmitter monitored AM, FM and SSB is received. There are coaxial inputs on this that come from AE7, and this board is the audio processor. The audio processor also talks via data bus to the audio gen board, which is the next board beneath it. Now that board in itself shares a common data bus with all the other boards, including the microprocessor board, which sits in the frame, not in this cartridge but on the bottom of a test set, does the digital microprocessor board. And they're all interconnected with a ribbon cable. So we've got a modems, digital systems modem card, we've got the display board, which just drives the CRT, and I'll go into that in a moment because it doesn't just do the display. We've got a modem, we've got an audio generator board, and obviously the audio processor, and with a few other things sandwiched in between as well, which is for things like the digital cellular modems, etc. Now, I started replacing all these boards, and one by one I've changed them, because the manual technical description talked about different parts of the audio processing being carried out by digital signal processors on certain boards, mainly on the A3 audio processor board, and obviously the audio gen board, and these two boards share common functions between them. But also in the technical description was some detail about the display board, which is right towards the bottom of this cartridge, which I also replaced. And the display board does actually deal with the FFT functions for the scope. So this is a display board here, this, and we've got digital signal processors and ASIC, application specific integrated circuits, and FPGAs mounted on this board, and they communicate with the other boards via the I2C data bus, which is a serial clock, serial data and ground connections, like 3 wires which is in the loom connecting each board, which communicates with this bus. And this bus is the major communication protocol and system that's used throughout the instrument. And what happens is that the display board doesn't just display and generate the characters for the CRT to obviously display to the user. This board has two functions. It's an oscilloscope board where the FFT, fast Fourier transfer calculations and processing is done on one side, and the other side then is a graphics generator, which also shares some of its characteristics and its function with the microprocessor board. So the microprocessor board shares some of the audio, FFT and scope and DEMOD processing of a digital measurement that's taken place earlier on the other boards, and shares that functionality between both boards. Now this is only revealed in a passing comment in the service manual. The service manual mainly references the A3 board, which is the very top board, which sits at the very top of the cartridge, which is this board here on the very top, because that's where all the audio connections for all the instrument connect to. And then it talks about the audio gen board as well, using the DSP functionality, and then that then communicates over the data bus to the display board, which carries out the FFT measurements and filtering, etc., that's been pre-done, converts the digital codec, if you like, or the digital interpretation of the audio then back into what will be a graphical example to be displayed on the CRT. So having replaced all these other boards in this cartridge one by one after the other, right the way down, obviously the technical description seemed to indicate one of these boards would obviously be the culprit, being mainly the audio processor side. So that's why earlier in the video I got very frustrated at the fact that, having changed the most core system boards which deal with the audio side, it still didn't solve the problem. And this is merely and simply down to the fact that there's one single sentence in the service manual, which is quite hard to find. It is in there because I've read it, and it talks about the FFT functionality on the display board, which is this board, is shared with some of the digital signal processing that's on the main microprocessor board, which is this board here. And so we've ended up basically changing every bleeding board in the test set by the microprocessor board, which is the last one I've just replaced out the entire cartridge, a stack of sandwich of boards. So I'm quite annoyed at that, the fact that it's been the last board in the test set, and this is right at the bottom of the test set, which we'll see in a moment. So it's very annoying that I've gone to all that time and trouble to try and diagnose that issue. So there is a fault on this board. Now this board itself is the one that's come out the radio test set. This is the board that was in it, it's faulty, and I've got a spare working one which I've installed myself in the test set to prove that the fault is now sorted. Now the thing is, I've now got to find the fault on this, really, find out where that's gone. I'm hopeful it's just something basic and minor. Could be a dry joint on the board, or one of these chips. Could be an electrolytic capacitor that's gone dry somewhere, or some minor problem. Hopefully it's not a major fault, because I don't want to have to go back to a customer and say, well, we need a new board in there, because that's what's going to cost quite a lot of money. So I'm hopeful now I can analyse what's on this board and find the fault. Now having said that, I do have to now go through all the software calibrations again on the Marconi to ensure that there aren't any other faults elsewhere as well, because as I say, this test sets have multiple problems with it which we've found along the way, and I don't think we're out the woods yet insofar as multiple faults. I think this is the answer to the TX modulation fault, but there are other faults on the test set I've noticed, little subtle things which we need to iron out and which may be sorted in the calibration. And it could also be a fault on this board that's also causing those calibration issues as well, but we'll go through that together next. So quite an interesting journey so far. I even went to the extremes of replacing the calibrator board, which is A8, which is this board, and this sets up all the audio cals for the test instrument to use for its modulation, demodulation, and also provides the alignment for the 0 dBm power reference setting with this potentiometer, as well for setting up the power level for the power meter calibration. So with that being the calibrator board, this board, I thought we'll change that, because in the service manual it does go into a lot of detail about the way that the instrument calibrates itself insofar as the DEMOD's concerned, is it doesn't use an RF signal and it doesn't modulate the RF signal either in order to calibrate the DEMOD side. However, what it does do is use the FM carrier later in a different calibration mode, which is for calibrating the receive signal generator's FM modulation component. So during the transmit modulation measurements that it does in calibrating the DEMOD under the software, which is accessed by the Marconi service menu, in this section here, which is the scope and FFT and DEMOD, these particular calibrations are done by the test set essentially generating from A8, which is this board here. This generates it in essence, or sets up a 1 volt at 1 kilohertz signal, which is for the AF gen outputs. But what it does, the test set A3 board, which is this board at the top here, this one, it switches that audio signal from the calibrator board into the A3 processor board, the audio processor, and that's on the same input path, the same input switch as we saw on the diagram earlier, than the signal coming from AE7, which is the FM DEMOD board underneath. So in that calibration alignment, it's not using an actual RF signal, it's not generating an RF signal and coupling it back to itself and modulating that signal and then taking a measurement of it to calibrate itself. It doesn't do that. It uses an audio signal which was representative of an FM demodulated signal, and that then is how it calibrates and it takes its measurement. And obviously we have potentiometers on AE7, which is again in the alignment procedure, which says to set up the absolute AM and FM DEMOD levels. That's what we would use for that, and there's a separate test later in the manual which demonstrates how to do that. But this modulation thing is very, very important, because when we go into dealing with the signal generator side of things, the signal generator calibrates its RF levels throughout the entire frequency range of the instrument, and also at 1 dB points across every frequency. It takes quite a few hours for this to complete when you run that. But what happens is, as part of that RF alignment, it generates an RF signal and a level, and it alters that as across the range of the instrument, but it also alters and puts on the mod as well. And part of that test is that you link these two ports together. And so what it does, it generates an RF signal, puts a mod on that varies in amplitude from a few hundred hertz in frequency and a few hundred hertz in deviation, right the way up to over 100 kilohertz mod, different frequencies, audio frequencies, and it calibrates then the signal generator's capability for mod gen. And so without the TX monitor side working, which is the problem that they've had with the instrument, most of these cals won't work, because some of the cals require the internal 1 kHz audio signal routed through the audio board, representative of a transmit TX deviation, be it AM or FM or SSB, and other alignments actually rely on a proper RF test, where we're generating an RF signal on one port and coupling it into the other with a jumper cable, and then the test set performing an alignment against a true RF carrier with a true representative FM modulation. And so in order for that to work, the TX deviation side of the TX measurement must be accurate for it to calibrate the receiver or the RF signal generator. So it's a domino effect. If you get one of these particular important cals, which is like this critical element here, which is a TX mod not working, other cals don't work. So other parts of the instrument then won't calibrate properly, and then it won't measure right, or it won't produce the right signals. So that's a learning curve, is that, and quite a complex way of doing things insofar as the instrument's concerned. But after reading several hundred pages of the manual, you only get to know that information, and you also begin to understand more fundamentally of how the test instrument works insofar as its calibration. Now, there are other tests as well that are part of the calibration routine, where the internal attenuator module that sits behind here, which we've seen on the side of the instrument, does have an internal RF relay which switches in a power reference, obviously for the 0 dBm RF power measurement, but also it has routing inside there to switch in the RF signal generator internally to the TX monitor side without having to put a jumper cable in. So some tests you need to have a jumper cable in, some tests you don't need any RF jumper cable in, but it's still doing an RF measurement in the cal, and then other tests and calibrations use the internal audio reference as an RF measurement just for audio purposes. So there are several different elements to the calibration requirement on the test instrument. So very odd, but anyway, I'm pleased that we've got to this stage, because now we understand that it was a digital signal processor that's obviously conveying information to the microprocessor board, and the microprocessor board again processes some of the FFT functionality and shares that with the display driver board, which carries the scope circuitry and the FFT bar chart and all the wherewithal for the audio processing side. So quite a lot of the audio is split across several boards, either for transmit or receive measurements, and that then causes mass complications. So what I'm going to do now, we're just going to look in the test set to explain the boards and where they are and what we've done so far. Okay, so I just wanted to show, having done some of the calibrations that were in the deep level Marconi signal setups, the deep level one, we can go through the signal generator, power meter, spectrum analyzer, etc. I've been doing some of these to try and recalibrate it, but with obviously the new microprocessor board in, because obviously you have to redo all the cals again. We're currently generating 5 kilohertz deviation at 100 megahertz FM on the HP Agilent radio test set. We're feeding that here on the low power port, and we are receiving 5 kilohertz mod. Now if I up the we set an increment on the HP Agilent to go up in 5 kilohertz of increments, so we can test the auto ranging. So obviously that would be 5 kHz obviously, and if I can press the button on the good old test set. So let's go right back to 0. So that's 5 kHz deviation obviously. I set it at 5 kHz increments, so that's next increment 10 kHz. So you can see the auto ranging's automatically taken place. That's 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100. You know, this test set can measure up to 100 kHz deviation. I'm taking it over that now. 120 kHz deviation, which is a maximum. Now if we go right back down to, you can see then it'll go to the next range. There we are. And then again the next range at 5 kHz. Now if I set an increment of 1 kHz, if I can get it to do it, 1 kHz, and as we start to increase, you see below 10 it drops to the next range, then we start to come down, then it goes to the next range, and so on and so forth. So that's like 1 kHz, 2, 3, then it jumps to the next range, 4, 5, 6, 7, 8, 9, then it should jump again. There we are, to the next range. So that's auto ranging's working. Obviously just keep going with it. Again, next auto range. So that's quite interesting. Obviously on the oscilloscope it's manually ranged, so we'd have to obviously increase the range there. We've got 4.2 kHz deviation measured there correctly as it should be, and so we can, you know, obviously adjust that correctly as we can see. So that proves that the ranging's all working, no problems. So very strange. So having proved that now, we talked about it, but at least you've seen the proof. Let's just have a look at this logic board and look at that in a deeper detail. Okay, so this is where, if you like, the heart of the instrument is contained in these cluster of boards in this cassette here. So this is where all the measurement functionality of the instrument comes into play here. Now for this cassette to be removed, there's obviously 2 screws that hold the cassette down at this end, but not only that, you have to remove some audio cables that connect to 2 different sockets here, and they go off somewhere. And then what will happen is it'll allow you to get the cassette about that high up, and then it'll stop. Because if I open this cassette further, because I've sort of done this already, this loom here that you can see, that plugs in the side there of the cassette, which I'll show you exactly which board that plugs into. It's quite difficult really to see where it goes because it's not obvious, but that loom plugs in there, so it'll restrict how far this cassette comes up, and that cassette will only come up so far. So don't try and yank it, you know, if it won't come up any higher, because there's something obviously wrong. If that's the case, you've left something plugged in. So anyway, we'll open it up like a book. As you can see, there's a cassette full of boards there, lots of boards, which we've replaced. Now the board I've just replaced is the board at the bottom here, which is sunken into the bottom of the darkest depths of the test set. This is the microprocessor board, the main heart of the instrument, the controller, if you like, for the whole instrument. So all the wherewithal, the software and calibration and the processing is all done there. This board is called A7. I think I mistakenly referred to it earlier in the last section of the video as A8. It isn't, it's A7. This board is what's known as the front panel interface. Now, it doesn't just do that, it does other functions which I'll go into a bit later, because we've got a coaxial cable coming off it and obviously an adjustable potentiometer. and that sets up some calibrator output level, which we'll talk about later. So it's not just a simple front panel interface. We've also got the CRT, we've got the RF attenuator assembly there for the Sig Gen step attenuator, we've got the backup battery for the memory above it, for the user memories, for the RAM backup, and at the back here we've got a power supply, which both comes in and outside of a test set as a complete module, and then we've got the breakout board here for the power supply to diverge supplies off to different parts of the instrument. We've got the loudspeaker here in the bottom corner, just there, and then we've obviously got a bunch of coaxial cables which feed low level RF signals in and out to the PCBs on this cartridge, as well as audio AF signals. We've also got a loom assembly which delivers different logic data buses, logic levels, TTL, CMOS, and also the I2C data bus, the serial data bus. So if we explain now what all these boards do on this cassette, that will give you a better understanding. So right at the top then, this board here, which is what the manual alludes to, the main audio processor, is A3. So this board's A3, this is the audio processor card. And this is where all the FM and AM DEMOD SSB comes in. We've got a connector here where my thumb is. That's where the coaxial cables for AM and FM come in, and then other coaxial cables feed audio in and out as well. Beneath that board, which is the second board down, is a A2 board, which is again an audio processor board. So these two boards share the same functionality of one another, okay, sort of share the functions between them. The third board, which is just mounted above the aluminium frame, is the audio generator board. That's called A1, Alpha 1. So A1 is the audio generator board for the audio signals, okay. Now then, in the top here, just if we look in this area, where the aluminium sort of can is, and see if we can get a better view of that, just mounted on top of the aluminium can there on the inside, that board is the modem board. Now the modem board has some functionality on it which allows encode and decode of signaling standards like MPT 1327 trunked, cell call, CTCSS, sequential tone signaling, POXAG paging, all that sort of done on the modem board there. Then beneath that board as well, we then have, if you like, a metal section just there, and then we get to this board here. Now this board, which is this section here, that board is the display board. Now the display board not only drives the cathode ray tube, the CRT assembly, with character generation and graphical examples of user interface, but it also has the FFT scope functions on it, the fast Fourier transfer scope functions on this board, and that shares a common data bus then with the rest of the boards, and mainly shares its data with a microprocessor board which is in the bottom of the instrument, which is down there. So that's the display board and scope board, if you like, combined. The bottom board here is the PPH, RTP and TTP digital systems card. So this is available for 29, 66 and 68 models. So for example, you know, this is where the digital systems functionality for like Tetra, P25 if the test set's got that as an option, whether it does GSM, cellular, or whether it does 4G, LTE mode, things like that. That's all derived and generated on these cards. So depending on what test set model it is, for example, it's a 2968 like the test set that we've got behind, there'll be a different card on there for doing Tetra digital standards, etc. If it's mainly a 66 or 66A which this model of radio tester is. There'll be a digital systems card for GSM, DCS and other cellular carrier modes, etc. That will be on those cards. Now they all share that common data bus, data interface, and obviously you know, as the manual has progressed with the fault finding techniques that we've been using, I've replaced each and every one of them in turn. And obviously, as you can imagine, when you replace a card in itself, then you have to go through the calibration procedures again, which takes many hours each time you do a replacement card, because each card stores its data in the E2 on the digital board, the main microprocessor board, and obviously the cal data for those boards is held there. So the moment you replace these boards, then, you know, unfortunately what that means is that you have to recal, and it causes all sorts of untold issues and problems, as you can no doubt imagine. So yeah, so after replacing all those boards with my spares, we then find that the actual TX deviation side was resolved by replacing this board, much to my annoyance, because I would have expected that to have been the least likely culprit out of the whole boards, considering the audio processing and the digital signal processing that's taking place with the DSPs, FPGAs and ASIC devices that are mounted on these PCBs. I would have expected the audio processing boards to have been at fault, and I was wrong. It's on the microprocessor board. And yeah, that becomes clear more when you read the manual, because as I said earlier, there is a paragraph which talks about the display board, which obviously deals with all the character generation and the FFT DEMOD and scope functionality, sharing its data with the microprocessor board. And the microprocessor board has some more DSPs on there which also interact with the display FFT function, so that, if you like, the scope and FFT functions on both boards, so that makes it more complicated. And yeah, so a little interesting thing. So where we're going to go from here now is I just need to look at the diagram for the microprocessor board, which is the one that we took out the instrument, and I just need to familiarise myself now with this circuit and look now more at the audio side of things and see what the hell's going on. You know, is some of the audio being processed on here? Is it purely all digital? Is there some analog audio, or some, perhaps there's a reference coming in to this board in an analog form which has been compared against something else, perhaps in a digital form? I really don't know, so we'll have to look at the technical description on this and have a look. It could be, you know, there aren't many capacitors on here to replace, because when we look, these are obviously going to be supply decoupling capacitors, because this is where we've got the supplies, the -5, the +5, the -12, +12 coming in, and they're obviously getting smoothed out with these electrolytics. Looking round the board, I can't see really many capacitors apart from just these 4 and obviously these 2 here. So there's nothing obvious as such that stands out. I can't see any corrosion on the board, although it's dusty, it does need cleaning. There's nothing really I could see on the rear that would give any indication as to an obvious fault. So is it a dry solder joint maybe? You know, does some of these ICs need reworking? Is there a capacitor, one of these little electrolytic caps on some kind of op amp that does some kind of referencing for the audio side, or the auto ranging maybe failed? Have one of these transistors failed that do some kind of switching or something like that? Who knows? We're going to have to look at it and investigate. try and find out what it is, you know, but who knows? Is it a software problem in one of the DSPs, you know, where there's some issue there? I would doubt it, but you never know. It could be a corruption in the software. There could be all sorts of problems. There could be one of these ICs that's a regulator for the supply rails. I really don't know at this stage till we look at the diagram, but interesting. Let's progress and see where we get to now. Okay, so we've just cleaned up the board because it was full of dust. The original microprocessor board from this radio test set, and I've just been going through it with a little spyglass that I've got here, just having a look at the solder joints on these connections here, these sockets. There are a couple of suspect looking dry joints, but nothing to write home about, nothing that I could certainly say would cause a fault. I've had a look at the ICs as well, as the pin goes underneath around the ICs, and they all look to have enough solder on them. Some of the pins are very difficult to see in regards to the quantity of solder that's underneath, but it could be they need a resolder perhaps, you know, there's a bit of dry solder on them. These capacitors here do the supply line filtering, and these are series inductors. I've just checked off camera the continuity of these inductors to make sure they're all functioning, and they are. So, and I would have thought if I'd have lost the supply line there, which is +5, -5, +12, -12, it would have stuffed the thing in a big way, but it hasn't done, because we haven't lost a supply there. There are obviously some other capacitors as well. This is the serial interface chip for the rear socket RS232, so I don't suspect these caps as causing that kind of an issue. This group of transistors here in this area is used for switching the attenuator relays in the attenuator module that we saw on the side of the test set. So all the RF relays, both in the main input attenuator module as well as a step attenuator for the RF signal generator, all controlled by these transistors there. And we've got some op amps and various other things which again have got a capacitor associated with them. These capacitors here and these two are associated with the supply lines for these devices, so don't suspect those to be an issue, but I will remove them anyway and check them. There's only really about 3-4 capacitors on here that I would suspect could cause an issue with the data side of things or some kind of reference. The only other thing I could assume would be dry joints on the connectors that go off to the different boards. Also perhaps dry solder joints on the pins of these ICs, but it could be, you know, a multitude of things. There aren't many through holes or through joints. There are one or two where the pins go through the board from the top on sort of these kind of ICs, and there's an eyelet at the top as well as at the bottom, and there's only a connection on one side, and some of the solder on those looks a bit crusty, but nothing super major. I can't really see anything that sort of stands out as obvious, and I've gone over the board with a fine tooth comb looking at it through the magnifier, and I can't see specific issues on the board. So is it a software corruption within one of the ICs? Obviously this is the main processor, the 6800 Motorola processor, but then we've got these Altair DSPs, digital signal processors. These are the things that are doing the work, so potentially there could be an issue with them, but I don't know if it's a software corruption or whether it's just a dodgy supply to something. Now, interestingly enough, on this board, because we'll look at the circuit diagram in a moment, the supplies that are coming in on these pins here, don't go to a separate voltage regulator before they then go to the ICs. Not that I can see at the moment anyway. The 5-volt rails go directly from the external power supply module that feeds supplies in here to the ICs directly. Whereas you get on a lot of equipment like the older Marconi test sets, etc., you'll get voltage regulators on each board. So obviously then you'll have a 5-volt and 8-volt voltage regulator, possibly even a 3-volt voltage regulator for providing power to the microprocessor, and that will be on the board itself, and each board will have its own cluster of regulators. On this design it doesn't look as if that's the case. It looks as if the external power supply at the rear of the test set feeds power directly via the power conditioning circuits here straight to the ICs. So obviously if you get a problem with the power supply, it glitches or it blows up and it over voltages, then it'll stuff all the boards on the test set, because obviously the voltage is applied directly to the ICs, not via a protective voltage regulator. So that seems to be the architecture of this anyway. But as I say, there's nothing stands out. There's no dry joints really that are obvious, or broken pins, or something obvious like a cut track or a damaged PCB. There's nothing obvious like that. And likewise on the other side of the board as well. I can't see anything here, any damaged surface mount components, resistors, transistors, etc. that have packed in. No smoky sort of burn marks in the board or anything obvious. So something strange. So is it a dry joint, something simple, and we just have to spend time resoldering the ICs, or is it you know, something really simple like one of these electrolytic capacitors that's dried up, but there's no sign of any leakage around the base, and these are synonymous for leaking. There's big corrosive elements around the thing, but again, I'm not going to dismiss that out of hand either. It could be something as simple as that. So yeah, I think we'll look into it a bit further with the magnifier on and see what we come up with. I think that's the only way we can proceed. Okay, I'll just give this circuit board a wash with isopropanol alcohol cleaner and a toothbrush with fine bristles, so it gets in between all the little pins and things and washes it out. Took some scrub and it was filthy, the board. It was full of fluff and dust and all sorts of terrible contamination. So I've cleaned it on both sides of the circuit board as well. I've thoroughly done that. So I've just had a quick look round it just to see if I can see anything obvious as such, and there's nothing apart from one thing that stands out, which I'm going to point out in a second. Well, a couple of things really. This connector here is where the connections for the other boards connects to. There's like ribbon cables plug here, and that carries all the data bus connections and everything off there. And when we look at that a little bit closely, the pins on this side of the socket look relatively good, to tell you the truth. They don't look bad, and if I just get in a bit closer with the camera, I might be able to see a bit better when I turn it round. But these all look okay, reasonable. I will resolder them all anyway because of the mechanical stresses and things that have been on them. But if I turn it round with the board the other way, so we can see those connectors again. This one, it doesn't do it justice on camera really, but to the naked eye, this one looks a bit dodgy. The rest of them look okay roughly, but that one as well there doesn't look like it's got much solder on it. Looks like it's dry. The solder, when you look at it under the magnifier, it looks weird. It looks like as if it's got some kind of like a crustiness to it. And then the other thing that I saw as well is IC60. So I'll just zoom out, see if I can find IC60 again. And IC60 is down here, I think, somewhere. That's it. So again, hopefully the camera will do it justice, but if I zoom in on IC60, as you can see there, it looks okay on this side of the IC, and that chip next to it as well, IC3 I think it is, and this is IC60, IC59 looks okay. But if I just turn it that way, you might be able to see and I might just have to try and zoom out a little bit so we can get that more in better definition. This second pin there is discoloured, and it depends on what light, how you catch it, but it definitely looks corroded, does that connection. I'm not sure what IC60 does yet, but we'll look at that. It might not have anything to do with the fault condition that we have. You know, that's always the thing, you start delving into other areas. I could take the IC off, clean the pins up, and also what's on the PCB, and then resolder it. I can do that. The rest of the ICs, that IC looks okay. These pins on the IC, some of which are soldered through onto the top there, the eyelets on the top as well as on the bottom, and sometimes you can get sort of cracks or dry joints around the top of these, because sometimes on some boards the eyelet goes all the way through the PCB from top to bottom, you know, like these things, that goes all the way through. Sometimes it doesn't. Sometimes the eyelet only goes a little way in the board at the top, and then the eyelet underneath only goes a little way in underneath, and then it relies on a solder blob in between in order to connect the two together. So I don't think it's the case on this Marconi thing. I think the actual eyelet goes all the way through, but I've seen some which I'll point out on this board where it looks like as if the solder does come all the way through. And again, the IC on that side looks okay, but you never know, you know, with some of these connections on the top, like these, if a solder's actually broken within the thing with the heating and cooling down, the heat and cooling cycles, and all the ICs look okay there. That socket PLA looks reasonable, can't see any problem with that. As I say, I've had a look at these ICs as well where the pin goes under, it curves under, you see, and then you've just got solder up the side. And again, these DSPs, etc., there's looks like as if there's no soldering issues on there. These smaller ICs here look okay, and so does that PLA and PLC. I can't see anything wrong with that. Again, these capacitors, that's the RS232 driver for the serial port, so I'm not really concerned about that, but you know, I will check the caps anyway. That looks okay, that IC, can't see a problem with that. These couple of ICs, we've got the pull-up resistor network in these things, and then this IC, can't see any corrosion or anything around that. Then we've got the power conditioning inductors and capacitors. These definitely need a look at, because that's where the main power rail comes in. Again, these you have to look round all these chips, obviously, which I've done, but these chips all look like as if they're being soldered down pretty well, to be honest with you. I don't think there's any issues with those, but we may end up getting into such a stage where we're that desperate we will actually need to resolder them, you know, just on the case. Again, you know, we're back to these sort of connectors again, and you can clearly see there that there's definitely not much solder on some of those pins, and it does look okay to some extent, but just for continuity I'll solder those. Again, that IC looks reasonably well. I can't see, I just turn the board round. Again, you know, when you look down these sort of pins, you know, they look all okay. Can't see there being any issues with some of these. But of course, you never know. Could be a little crack there or something like that. Sometimes you do get things like that. It's not guaranteed, of course, but you know, one never knows. Just seems strange, must admit. This fault, for it to be like it is, could it be down to that corroded pin on that IC60? Potentially. We'll have to look at the diagram to see what that does, but what involvement that possibly may have. It might have an indirect involvement, maybe. This external memory socket isn't used, this thing, so we're not need to worry about that. But again, it's, you know, these are all the sort of RAM ICs, etc. The memory for the test set is all there. So I can't see, you know, anything obvious as such, apart from just those couple of observations really around the socket. So they seem a bit strange. Again, more memory there, the Atmel EEPROMs. These are the transistors that control the step attenuator and the input attenuators. Again, we've got two capacitors there, need checking. Another one here, and this one. This is some involvement with this IC. So yeah, the only thing I can find then is obviously IC60 and that pin, which looks like it's tarnished. But again, it depends. It looked worse before I cleaned it up, to be honest with you. That second pin there, it looked worse than it did before I cleaned it. But now I've cleaned it, it's not as bad. But there's still something not right about that. So there could be more corrosion under here, something that's gone off. So strange. And we'll just have a look underneath again. Nothing obvious as such. Can't see anything that stands out. Again, particularly interested in the sockets underneath to see if there's any dry joints on them or anything like that. Anything that sort of shouts out at us, hey, come here, look at me, you know, I've got a cracked solder joint. And the surface mount components and everything, I've had a good look at those, and I can't see anything, you know, wrong with them. Nothing obvious, no cracks, no damage, you know, where somebody's had the board out and dropped it or banged a tool into it. Sometimes you get that, and components scrape off the board, you know, you get chips on them and breakages. And can't see anything wrong with those sockets there. Again, just skewing round. But you can see in places there's a solder connection going through, like there, that eyelet there, little solder connection. There's a few little ones that you can see, so whether they're worth resoldering. Again, another example just there, look. And there's a few examples around of that. Again, another one down there in the bottom that's got solder through it. So is it because, are these potentially dry joints maybe? You know, not every eyelet has got solder through it, but some definitely do. So is that a reason for that? Are they dry? Are they cracked? You know, again, over here, there's one there. So, and then there's a couple there, look, with solder through them. So are they part of it? Another one there. Another one there, look. So, you know, again, do these need soldering? Is there some issue with that? So, but all looks okay, to be honest. Nothing obvious. But there again, there never is anything obvious, is there? It's always a mystery tour. Again, we've got quite a few. That looks like it's been partially soldered, obviously. And then these. Again, these. So definitely some resoldering to be done on this. Very time consuming, obviously, trying to get through all that. But there's nothing much I can do other than just try and do the obvious, you know. It doesn't look like as if anybody's resoldered it before me, so that's always a good sign. And again, there's some through solder on there, but yeah, I don't know. Might be clutching at the straws with this one, I think. But we'll see what we can do, where we can get to with it. Right, start soldering, I think, and have a look at the diagram as well. Okay, so what we've done, we've removed a couple of capacitors off the board and checked them for proper capacitance, and I found that the capacitors that I've taken off the board have all been okay, and I've been able to do some in-circuit testing with some of them and they've been fine. I removed this capacitor as obviously we suspected that. These are really supply line conditioning capacitors which are also okay. All the caps I've removed so far have all shown good signs and good value, so I don't suspect any of them. We have two fuses down here as well, which are these sort of resettable fuses that automatically reset once the fault condition's gone, and they're fine. They're reading just a couple of ohms across them, so they're no problems. So I've gone back to this IC60 here, and I've just removed it with a hot air gun that was placed here and put it on top of this chip just for the time being, because we had a problem with this sort of leg down here. So what I do intend to do is to solder that, and we'll just take a closer look at that under the magnifier and see whether I can get this magnifier to show us the pin better. But it looks okay actually, but it's just a bit it was a bit tarnished, and perhaps it is a bit tarnished underneath the IC itself, and on that pin there's a bit of tarnishing on it. Might not be making good contact underneath, so I just thought I would you know, just try and do my best with that to try and clean it up and resolder it back, and then I'll be happy with that, and that rules that out. I've just resoldered all these sockets as well, put some flux on and then resoldered them along with this socket here. So hopefully, fingers crossed, once I've resoldered that IC back, I'm tempted to put this board back in and test it just to see whether it works, but we'll have another inspection just once I've got that IC in, because I could start resoldering all the chips, but to be honest they all look fine. I don't like as if there's any major problems with the soldering on the rest of the ICs, and I'll be just doing it for the sake of doing it. All the plugs and sockets are all okay now, so but we'll just put that chip on and then we'll have another evaluation. Okay, so I resoldered IC60 back onto the board, and I decided what I'd do is I'd resolder the DSPs, which are essentially these three ICs. I've already resoldered this one. I'm just going to go around, just sort of done two sides on this. I'm just halfway up this side at the moment, and I'm just reflowing it. The pins, just making sure that the pads on the board are flowing as well as the pin on the IC, and then I'm looking at it with a magnifier as well at the same time, so that you know, I can keep an eye on the pins as I'm going round. You know, that's the main thing. I'll probably do the three DSPs and then the microprocessor as well, because it could be a logic pin on the microprocessor that's not connecting properly, and so I'm just, you know, doing the usual, that's all, just preempting any possible dry joint, solder joint, etc. I'm just making sure the pin moves, you know, back and forth on the IC on those three there, because the solder didn't flow well. There's definitely some connection, some solder on the pins here, which is quite brittle and old, because some pins are quite easy to solder and others are quite difficult to get the solder to melt. So only the odd pin though here or there, but that could be, you know, necessitate a dry joint. But so far so good. All the pins look as if they're well soldered. You know, there isn't an issue there. So that's that IC done. So that's two ICs done now, that one and that one. And again, just deal with this one now. Now, because I've put IC 60 back on, which is down here, this IC. I'll put that back on. That did have a tarnished pin on one side, so potentially it could be, you know, could be something to do with it. I was hoping really that the resettable fuses, these two devices there, F1 and F2, had FS1 and FS2 had packed in. I was so hoping that the ohm meter that I put across them would be reading open circuit, and that would be like such a godsend really, in order to, you know, sort of like, wow, that must be the fault, and then perhaps find a shorted capacitor somewhere or something obvious, you know, and then get it going again. But, you know, through something as basic as a fuse being blown. But I don't have that luck, I'm afraid. You do see it on other YouTube channels, that kind of look, but on my YouTube channel you definitely don't see that. And I am, you know, one of these people, me, where I just don't seem to get that sort of easy look. All my faults that I tend to deal with are all faults that other people have had a go at beforehand, and in this case, with this test set, somebody's had a go at it and then either given up or replaced boards left, right and centre. And I'm sort of proud of myself really that we've got this far, because they're quite difficult test instruments to work on at the best of times, and I do hope all the guidance that I've given so far will help somebody else further down the road in trying to resolve some of the issues and things. But again, you know, you win some, you lose some. Sometimes, you know, you can't repair everything that you get, but other times you're successful. You know, 9 times out of 10 you can get things repaired. But it could be here we've got a faulty DSP chip itself. It may not necessarily be an external component that's failed. I'd like to think that it would be unlikely we'd have a chip fail, but I have had it before on instruments where ICs have failed, and I did have that indeed on a Marconi microwave test set. Although it was a display issue, it was a multiplexer IC for the display, the LCD display, and the only way you could get it to show the fault, well, to stop being faulty, in other words for the display image to come decent again, was to spray circuit freezer on the driver IC. And the driver IC obviously started to work when it was frozen, and then when it warmed up it started to have a corrupt display again. And that IC was only about £3 to buy, it wasn't expensive, so I replaced it, and we managed to get it going, you know. But these ICs are far more complex than that, you know, way more complex. So the chances of being able to get this going by replacing the IC, and besides which these ICs are probably not available anymore, and they will need reprogramming. They've probably got some firmware loaded into them as well, which needs to be flashed into them. And of course you can't do that unless you've got the programmer. And there are header pins on the board, I've noticed, in places for serial clock, serial data programming, and got the RxD and TXD paths on them. So it's obviously, you know, Marconi would flash them once the chips are put on the board. So yeah, it's a shame really, it really is, it's a shame. But it's just one of those things, I suppose. Right, we'll carry on resoldering and we'll come back when we've done it, and then I suppose we're ready then to install it back in the test set. Okay, so I spent quite a few hours now soldering all the ICs up on the circuit board, all the DSPs, all the big chips, including the processor, the driver ICs and gate arrays. I've done all these as well down here. I've not bothered with the memory side because the memory's not got an issue. if so, the checksum LEDs had come on, and we haven't got a problem with the memory itself. So everything else has been soldered now. I've gone through the whole PCB and resoldered all the ICs apart from just the memory. I'm not bothered about that. So I think it's now time to put it back in the radio test set and see if it works or not, and take it from there. Okay, so just one final inspection before we insert. Obviously, as we can see, you know, we've managed to resolder these ICs, and obviously one of the challenges of soldering these devices is not bridging the pins, you know, that so easy to do, and we've made very careful soldering of these ICs. So I'm just having a quick inspection, but having resoldered practically every IC now on the board, other than the memory ICs here, I think I've more or less done what I can. This is for the external RS232 port, and these capacitors are charge pumps, act as a charge pump circuit for the RS232 as well. So don't suspect any issues around that. They're the power conditioning caps and the series inductors with the power socket here, and we've obviously resoldered the microprocessor as well, the main central CPU, and that's all the pins on that are all looking nice. I've been around the board already, so done what I can there. And one of the interesting things is, because there are 3 digital signal processors, there are 3 header sockets here, and I'm sure that's how Marconi flash those digital signal processors, via these sockets for each of the DSPs. And obviously we've got the microcontroller side there. So having resoldered all 3 DSPs and this DSP as well as the microprocessor system, we've got another DSP there which I've resoldered. I would think that it's now probable to put the unit back in and give it another whirl and see what happens. So fingers crossed, when it goes back in it works. I certainly hope so, with the amount of time and effort that I've spent on it and checks of the components. I've done some testing with the multimeter on certain through holes, etc. You know, on these little through holes, etc., just to make sure they connect through the board where they're soldered underneath. But I can't see anything other than that IC60 that we had earlier, which was this IC, which I had off the board. I cleaned the pads up and then reassembled that, put that back on, and soldered that back in place. So yeah, I think we're good to go now with it being back in the instrument, and see what happens. Hopefully, fingers crossed, it'll work. Okay, I'm just looking at the underside of the board now, starting in these corners. I'm just looking for the obvious, like cracked or damaged tracks and things like that, just to see if I can find anything, damaged components where the board's been removed and perhaps bashed or chipped against something, and that often happens, especially when somebody else has been in it. I have had some very strange things in the past, especially when other people have looked at PCBs or had them out where they've caused damage. There's been solder slithers, you know, where somebody's flicked the solder off the end of the soldering iron and it's ended up picking up a slither underneath the board, and that's then caused multiple issues. So I'm just looking for the obvious, really, and just checking these components. Now these islands that you can see, these little vias that go through the board, that occasionally have solder in them, I'm confident when I've looked at it that that's been picked up as part of the solder bath. They've not been deliberately soldered, these little islands. They're just a product of the soldering process. So they are actually tinned all the way through, and that looks okay. That's just a pin connecting there. So we're looking under a magnifier at the moment anyway, so just keep going round having a look. Again, these all look okay. All these pins look alright on this IC here, connecting through. No obvious dry joints. Yeah, they look okay. Can't see any damage to the board either, you know, a big scrape across the board. Again, seen that happen a few times in the past where somebody's gone and scraped a screwdriver, you know, slipped with it, and or a scalpel blade or the soldering iron, they've ground it into the PCB, and you know, and it's caused damage. Okay, can't see anything really obvious. No burnouts either. Looking for components that are charred and burned out. Something else that sometimes you get, you know, where things have burned up, excessive voltage, etc. But I can't see anything there. It all looks okay to me. But you never know, because we are clutching at the straws with this one. You know, we're obviously trying to find out anything in particular that could potentially be causing the issue. No, can't see anything there. There's no cracked capacitors as well, these chip capacitors. Looking for cracks of those. The fact is, you see, the audio, the bar chart representation is done through the digital signal processing. It's not actually an analog audio feed, and I don't know what that is. Looks like some contamination by the look of it. I don't know what that is. That's just a bit of wax or something off the PCB. So, you know, sometimes you do get issues where somebody's dropped something in the test set while it's been repaired, you know, and you only need a metallic object to drop inside, like a screwdriver or a screw that's come loose, you know, that you've got on the end of a screwdriver while the test set's powered on, and that drops in, shorts some pins out, then it blows the logic gate array in the IC. But you see, the digital audio, well, the audio representation for the bar chart's carried by the DSPs. It's a digital representation. It's not an analog signal that's coming in. It gets the analog signals dealt with on the A2, A3 board, and then it's converted on the data bus, obviously via digital. So it's converted from analog to digital, A to D conversion, and then what happens is then it comes back through the data bus onto the control board, you see, and then what happens is the control board itself then makes a graphical representation of the audio, then which is then fed back to the display board to then be displayed on the CRT. So we're not really dealing with any analog audio on this board. It's all the analog audio is dealt with via the A3, A2 board, which deals with all the analog signal processing to digital, and everything's conveyed on a data bus. So I can't see anything at all wrong on this soldering side on this board. So that one's a bit skewed, and it looks okay. So it's more than likely going to be some kind of a perhaps a damage to the ICs, you know, and we'll just clean the flux off these pins, I think, as well, and give them a clean now. But I can't see anything that stands out as obvious, but just been and checked a few things, that's all. You know, I just need to be right in my own mind as to what potentially could be the issue, but that's all we can do, is just keep going round and just checking, because you never know, sometimes you can find things that somebody else has done and you end up you know, dropping lucky. It's just one of the ways of fault finding, but yeah, we're at desperate times now with this one. So anyway, we'll check the rest of the ICs there. That looks okay. Now that's the IC that I removed earlier, and that's all okay. Oh, looking good. That's a pull-up resistor pack, that. No dry joints on there, that looks okay. So, yeah. That's a little voltage thing there. Possibly a voltage regulator, not sure, that IC. That looks okay. Yeah. Right, so yeah, I think it's just a case now of reassemble it, and fingers crossed. We've done his final inspection. That's all we can do. Okay, we're ready to rock and roll. We've got the logic board back in again, and all the connectors back in situ, so all fastened in nicely. Power supply connection, all the other leads and everything are all there. Battery backup for the memory, all that. Just got this lead to connect to the one of the boards on there. Now it plugs in the side. That sorts that, and should power it up and see what happens. Everybody keep the fingers crossed. Okay, we've put the logic board back in, reassembled it obviously, and we've now got the HP Agilent producing 150 megahertz at 3 kHz FM deviation. We've got that connected into the test set, but as you can see there, the deviation is still reading low at just under 300 Hz. However, if I go to the scope, 2 kHz per division, that's reading wrong obviously. And then as we go to 4 kHz, reading even less, 8 kHz, and then wham, straight there. Then at 20, 40, 80, 200 kHz, etc. So it's not fixed it, I'm afraid, that resolder job. So the only thing I can do now is to use some circuit freezer that we've got here in order to try and freeze some of the components on the control PCB and see whether that works. So let's do that now then. Let's see whether, you know, because we are clutching at the straws now, I'll say that. So let's just position this test set and camera, and then we can do these tests and checks. So we'll leave it plugged in. I can see the front from where I am, and then what we'll do, we'll just go over now to the control board, and let's see whether we can make it work. So we'll start with some of the ICs down on this side down here, and let's see what we can get with that. So I think that IC60 were there. That's not made any difference. That IC there. Let's see whether we can get anything at all to occur. That capacitor as well, and the chip next to it. Nothing's changed. I'm just looking at the front. Just do these Just do a blanket area. Obviously that's not worked either there, so that area there's all okay. So what about these ICs here? That seems to go to the rear anyway, those two. I think they're for the GPIB output, so that's obviously not going to work. But not made any difference. So this IC there. Now, what about these little ones here? Nothing there. This DSP. That's not made any difference. Try that one. Nope. Let's try these ICs here, these little ICs. None of those. As I say, we are clutching at the straws with this. You know, because obviously it could be a faulty IC, a cheap IC. We'll do the cluster of these three. See whether they make any difference. Nope, still no difference. Right, we'll try that IC then. Still no difference. This cluster of capacitors and inductors, I don't see that being a problem because they're just supply line conditioning. They are, that's all they do. Nope. This IC. That doesn't look like as if it's made any difference. Still reading the same deviation at 270 Hz. This DSP now, we'll try that. Still nothing. This little IC down there, that yellow one. No. Microprocessor. Might cause it to lock up, but we'll give it a whirl. No. This DSP. Nothing there with that. And we've got some ICs just in this area down here, so we'll just have a look at those. We'll freeze them all. No change at the moment. So whatever's happened must be a serious failure, not temperature related. Then we'll do a blanket sweep over the entire board of freezer just to see whether there's any mechanical cracks in the board or tracks that have got some veer through whole thing that's perhaps expanding and contracting. So by spraying circuit freezer on the board, it'll shrink the board a bit and it might make them connect again, so we'll do that now then. We're going to do a blanket freeze all the way along. Let's see whether that does anything. Yeah, that's cold. You can really feel the cold coming up off of that. It's like opening an ice box. But no, not a dicky. Obviously we can spray around the connectors, but can't see that being you know, obviously we have the the other board in and working. So I'm afraid not. I'm afraid not. So, most unfortunate. Most unfortunate. But we've done as much as we can, I think. And very strange. What a weird fault. Anyway, at least we've tried. I think we'll have to look at where we go from here, I think. So, not wanting to dismiss anything out of hand, I wanted to go back to basics after having a little break from doing this test set and just focus more with my mind and read the manual again, the service manual, which, you know, is quite a lengthy process. And what I decided to do is, rather than throw the baby out with the bathwater, is I would just have another go. You never know, sometimes things can miraculously work out to your advantage when you come back and attack a problem again after a period of rest and thought. So what I did, I went into the Marconi, the menu, which allows us to get into obviously the secret menu here, which I've enabled by putting the password in. Then in here there's an option where you can go into clear mem, which is this button here, and then in there you can do all these resets. So basically you can reset the entire instrument and all the E-squareds, all calibration data, clear everything out, completely gut it. So I've gone through each and every one of these options off camera and I've reset it. That's taken me about an hour to do and wipe everything out. Then what I've done, I've totally reset the instrument and powered it off. And then what I've done, then I've gone into what is the cal values, and I've done every single one of these calibrations all over again, which has taken about 3 or 4 hours in total, because the Sig Gen takes about an hour to do. The audio and FFT ones take about an hour and a half roughly a piece to do. The others are fairly quick to do actually, but it's just those 3 that are quite difficult in time consumed. The spectrum analyzer about half an hour to calibrate that. So we've done all the calibrations. There's been no warnings at all as part of doing the calibrations, so everything seems to be fully functional insofar as what it thinks. And then we've gone essentially back right the way to the basics, again doing a transmitter test, and then I found the mod still didn't work. Well, that was a bit disappointing, because I thought that, you know, that was the last straw, if you like, the last chance of the possibility of being able to rule out, if you like, a software issue, where perhaps some cal data was held in resident memory somewhere that was that possibly could be corrupt, or that although earlier in the video I had done some resets as documented, so I did actually go into doing this top one here, factory reset, but I hadn't done most of the others, so I thought, well, I'll do all of them right from the beginning. So I was sort of got my fingers crossed really that when we went back to the transmitter test and we injected a signal in a 3 kHz mod, that suddenly I get the auto ranging working, because the auto ranging on AM works. We've seen that the bar chart alters, you know, when you're generating a signal, and as you increase or decrease the signal coming in amplitude, the bar chart self adjusts. So there's no problem with AM, it's just the FM side, unfortunately, something specific towards the FM, still reading 300 Hz deviation when the 3K is coming in. So we've really reached the end of the road now. I can't get it going. I've tried my best, I can't get over that last hurdle. There's something wrong, as we've proved on the digital board, which is obviously you know, being the cause of the problem, because my digital board that I fitted in as a service spare here from a working radio test set that I have, that digital board is this one here. This works in this instrument, as we've proved, so it's not just a speculation, a speculatory kind of repair where we've assumed that it's this. We've fitted this in this test instrument and proved it works with the auto ranging. So there's something specific on this board. So what I did, I went back to the schematics and also the technical description of this board, and looked at the detailed technical analysis of what all the components do. And it does talk about auto arranging in there, but basically it's dealt with through one of the digital signal processors. So there's no other external circuitry, if you like, to the DSP. It's got a latch that either goes high or low, whatever, to set the attenuators up for the, as we looked at earlier, on the AE7 board. So it'll either put a ×10 or take the ×10 attenuator out, etc., or divide by 10. So this is basically what's going off. So there's nothing really that I could pinpoint on this board per se that will point at a particular IC or a transistor somewhere, or a gate array external to the DSP, which is yet again causing this issue. And it's all dealt with via the I2C serial bus as well. So when it needs to switch attenuators on and off on the AE7, it will do that via the I2C. So we've obviously looked at other boards in the instrument that seem to indicate more of a function around the audio measurement capability. However, this board is the actual board that deals with that, because we've proved it. Now it does mention in the technical description that not only does the scope FFT board deal with the audio measurements, but it also shares that measurement capability with the DSPs on the control board, the microprocessor board, which this is. I obviously can't give the customer this board, because that would mean I'd be writing another Marconi 2966 off just for the sake of putting that board in. Excuse me. So it will be pointless doing that, obviously. So the customer is now faced with receiving a radio test set back that works 99% but can't read TX modulation on FM properly. However, everything else works, obviously, as we've proved. We've got it all calibrated and everything's working as it should be, but it's the TX mod measurement that's not working on FM. Now, if a customer were to get hold of another board, maybe off of eBay or some other outlet that they can buy boards or whatever, and fit that themselves, then that will be fine. It will get the test set working as indeed this one did. But I just don't have a spare board of one of these. I have other modules that go in the test set as spares, but I don't have a spare board. And it's important as well that you get a control board that's got the right version of firmware and software on it, which pairs with the other boards, otherwise there'll be data clashes and other problems. So it's got to be the right series of board, you know, sort of similar age. So that's another obstacle as well, getting spare parts. Are they going to be the correct version? Are they going to be the correct software level, the right level? Because there are two different software versions on these radio test sets as described in the service manual. So with that, I don't think there's much else we can do really. I've enjoyed the challenge. It's been a good little challenge as this. We've obviously seen that somebody else has been in this test set and hacked away at it, causing other faults as we've gone along, and we've rectified those as we've found them. But I've got a feeling that this test set's got a history which is quite hidden. I think it may have been used as a test set for hot spares in the past. Somebody's had a go at it, maybe swapping boards before me. There's definitely evidence of that internally, as we've seen throughout this video. So there's not much I can do now really. I've gone as far as I can go. Obviously labour time now is running into many hours, and there's just too many other things that I need to repair, and sometimes you've got to quit, you know, while you're ahead. Cut your losses and just move on to the next project. It's unfortunate, you know, because we've at least found the fault. I'm pleased about that, but I would have loved to have returned this back to the customer with 100% working condition, but I'm afraid it's just not possible. My own theory is whoever's been repairing this before me had a go at it has caused damage to the microprocessor board. I think either they've dropped something in the test set and it shorted some pins out on the DSP, or they've maybe bridged some connections in measuring with a multimeter probe and popped something, put voltage on an inappropriate pin, done something to the board. Anyway, it's got to be that case. It's obviously not deep enough for fault for it to flag up any checksum errors, because when we run, we've got these LEDs that are on the microprocessor board that notify us when certain bootstrap and the boot code doesn't quite run on the DSP functions and the FIFOs. So there's quite a lot of diagnosis that it does itself on boot up, which will be indicated by these LEDs if there was a failure. So it's not a deep enough level of a fault for it to, part of its self-check routine, to notice it. So yeah, it's a great shame really, but at least I'm satisfied in a way that I have found it's this board. I wouldn't have been happy giving the instrument back to the customer, albeit I can't repair it 100% and explain that, yeah, I'm sorry, I don't know what's wrong with it, but I just can't get it working. At least now I can confidently say to the guy who brought it me, look, you know, it's this board that's screwed, you know, you're gonna have to replace it if you're gonna get this test set going again, and good luck getting one of those. But the thing is, at least I've found out what's wrong. That's the most important thing for me personally. Anyway, with that, I don't think there's much more we can do now. I think we've flogged this to death. So I hope you've enjoyed the video. I've certainly enjoyed making it. It's certainly been a challenge as this instrument. You know, they can be quite challenging, these radio test sets, as you'll see with other repairs on these that I've done, and more videos to come on them as well on this channel. But yeah, very difficult is this one. It's not helped by the fact that someone else has had a go before me. It's a different set of circumstances when you're dealing with something like this, where somebody's had a go prior and you're sort of putting their faults right before you can actually start tackling the main issue. So yeah, just a shame really, not to worry. Anyway, you can't win them all, that's how it is. You get about 99% repair rate success, and you get, you know, one or two that slip through the net, and that's this in this case. Anyway, look after yourself, and we'll catch you in the next one. Hope you've enjoyed it. Bye for now.